Picture this, a vast, swirling cloud of cosmic dust and gas, glowing with ethereal light, hanging in the blackness of space like a celestial watercolor. This is the Orion Nebula, a place so vibrant and dynamic that it's often called a stellar nursery, where new stars are born in a spectacular firework display of creation. But what if this beautiful cosmic cradle is hiding something far stranger, something that challenges everything we think we know about how the universe works? Beyond its breathtaking beauty, the Orion Nebula is a treasure trove of the unexplained, a region where astronomers have witnessed events and objects that simply shouldn't exist according to our current laws of physics. We're talking about phantom stars that vanish without a trace, mysterious structures that defy logical explanation, and energetic anomalies that have left even the most seasoned scientists utterly baffled. This isn't just a pretty picture, it's an active, chaotic, and deeply mysterious corner of space, and the secrets it holds might just rewrite the textbooks. The phenomena we'll explore together are as diverse as they are bewildering. Imagine stars that flicker and disappear from one observation to the next as if they were never really there. Consider the possibility of vast, shadowy structures drifting through the nebula's heart, objects so large and dark they seem to swallow the light around them. We'll investigate powerful and unexplained sources of energy, bursts of radiation that appear from nowhere and point to processes we have yet to comprehend. And perhaps most tantalizing of all, we will look at the potential, however remote, for chemical signatures and atmospheric conditions that some researchers suggest could be indirect signs of life, hints that we might not be alone in this vast cosmic ocean. Each of these mysteries is a piece of a larger puzzle, a clue that draws us deeper into understanding the true nature of this incredible nebula. So, prepare to embark on a journey into one of the most fascinating and enigmatic places in our entire galaxy. This is more than just a tour of strange sights. It's an investigation into the very frontiers of human knowledge, a dive into the unknown that asks profound questions about our place in the cosmos. We're about to uncover 30 of the strangest phenomena within the Orion Nebula, each one a story of discovery, confusion, and wonder. From the phantom to the potentially profound, these are the cosmic riddles that continue to captivate astronomers and dreamers alike, and they are waiting for us to explore them right now. Our journey into the Orion Nebula's deepest enigmas begins not with a whisper but with a sonic boom. Moving through the nebula's dense clouds of gas and dust are runaway stars, stellar speedsters hurtling through this cosmic sea at incredible velocities. One of the most captivating examples is a star known as LL Orionis. This young, energetic star is not merely drifting, it's racing, ejecting a ferocious wind of charged particles out into space. But here in the nebula, it doesn't move through a vacuum. It plows directly into the slower-moving gas that permeates the entire region. The result is a breathtaking and violent spectacle known as a bow shock. You can picture this phenomenon by thinking of a powerful speedboat cutting across a calm lake. Just as the boat's bow pushes water aside, creating a graceful, arcing wave in front of it, LL Orionis creates a vast, crescent-shaped wall of superheated, glowing gas. This structure isn't solid, of course. It's a standing wave of energy, a turbulent boundary where the star's supersonic wind collides with and is dramatically slowed by the surrounding nebula material. The gas at this collision point gets compressed and heated to extreme temperatures, causing it to glow with an intense, ethereal light that makes these bow shocks visible to our telescopes. What makes these structures so much more than just beautiful cosmic art is the information they hold. A bow shock acts like a cosmic weather vane, clearly pointing away from the source of the strongest stellar winds within the nebula's core, the trapezium cluster. By studying the shape, size, and orientation of these arcs, astronomers can essentially map the invisible flows of energy and matter coursing through the nebula. They reveal the direction and power of the stellar winds, offering clues about the age and mass of the star creating them, and painting a dynamic picture of the immense forces that are constantly reshaping this stellar nursery. These glowing arcs are a direct, visible testament to the titanic forces of creation and destruction at play, a perfect starting point for our exploration of the Orion Nebula's many mysteries. But even as these titanic bow shocks reveal the immense power shaping the nebula, a more subtle and profound drama is unfolding nearby, one that speaks directly to the origins of worlds like our own. Deep within the glowing clouds, the Hubble Space Telescope made a discovery that forever changed our understanding of planet formation, the Proplyd or protoplanetary disk. These are not full-fledged planets, but the very cradles where solar systems are born, vast, spinning platters of gas and dust encircling infant stars, the raw material from which planets will eventually coalesce. The Orion Nebula is absolutely teeming with them, offering us an unprecedented glimpse into the earliest stages of a solar system's life. Yet this nursery is not a peaceful, sheltered haven. It is a cosmic crucible, a place of both creation and destruction happening simultaneously. These nascent solar systems exist in the shadow of colossal, brilliant stars, particularly the massive, searingly hot members of the trapezium cluster. These stellar giants blast out an incredible flood of ultraviolet radiation, a hostile, energetic wind that acts like a cosmic blowtorch on the surrounding Proplyds. When we look at Hubble's stunning images, we can see this violent interaction playing out in real time. Many Proplyds appear as delicate, tear-shaped structures with a bright, illuminated head facing the destructive stars and a long, dark tail of material streaming away behind them. That shape is a direct result of the photoevaporation process, where the intense UV radiation is literally boiling away the outer layers of the gas and dust disk, stripping material from the infant system and blowing it off into space. This creates a dramatic race against time for any potential planets trying to form within these disks. On one hand, the gravitational forces within the disk are working to pull particles together, building them up into planetesimals and eventually full-sized planets. On the other hand, the relentless stellar radiation is tearing the disk apart, vaporizing its material and dispersing it back into the nebula. The ultimate fate of a Proplyd depends entirely on this balance. If the central star is massive enough and its gravitational pull sufficiently strong, it can hold its disk together long enough for planets to form in the sheltered regions closer to the star, safe from the brunt of the external onslaught. But for smaller, weaker Proplyds, the evaporation process can be a death sentence, stripping away their planet-forming potential before it even has a chance to begin, leaving behind a bare, lonely star. The implications of this discovery are staggering. For decades, we assumed planet formation was a relatively slow, quiet process that occurred in the isolated calm of a molecular cloud. The Orion Nebula showed us that it can also be a chaotic, dynamic, and even violent event. It forces us to ask a fundamental question: is our own solar system the product of a serene, isolated birth, or did it, too, form in a bustling, radiant stellar nursery like Orion, having narrowly escaped being blasted apart by a neighboring giant star? The presence of these Proplyds confirms that the basic ingredients for planet formation are common throughout the galaxy, but their precarious existence reminds us that the path from dust to a living world is fraught with cosmic peril, making the existence of every planet, including our own, feel that much more precious and unlikely. Yet while the fate of entire solar systems is being decided in the brilliant glare of the trapezium stars, there exists a place within the nebula where light itself seems to be swallowed, a deep and imposing shadow that cuts dramatically across the glowing heart of the nebula. This is the great Orion Nebula's dark lane, a vast, winding river of cosmic dust so thick and dense that it completely blocks the brilliant emission from the gas behind it. To the casual observer, it might look like a simple void, a tear in the nebula's fabric, But this is no mere emptiness. It is a physical, tangible structure, a cold, dark cloud of immense proportion that holds its own profound secrets. This dark lane is composed of tiny, microscopic grains of silicate and carbon-rich material, similar in substance to soot or sand, but floating in the vacuum of space. These grains are incredibly effective at absorbing and scattering the visible light from the luminous gas behind them, creating that stark, dividing line of blackness we see in so many famous images. It serves as a powerful reminder that the nebula is not a flat painting but a complex, three-dimensional structure, with these dense dust clouds lying in the foreground between us and the nebula's main emission region. The dark lane is in essence a mountain range occluding our view, but a mountain range made of fine dust and frigid gas. The true mystery, however, lies not in what this dust hides from us, but in what it conceals within itself. These cold, dark clouds are not sterile dead zones. They are potential stellar wombs, shielded from the intense ultraviolet radiation that is evaporating the Proplyds elsewhere in the nebula. The interior of the dark lane provides a sheltered environment where gravity can work in peace. Deep inside these opaque cocoons, gas and dust can slowly, quietly coalesce, collapsing under their own weight to form the seeds of new stars. The very darkness that makes this region appear empty to our optical telescopes is the very condition necessary for a new wave of star birth to begin away from the chaotic violence of the nebula's core. To lift this cosmic veil and peer into these hidden nurseries, astronomers cannot rely on ordinary light. They must turn to different eyes on the sky telescopes that see the universe in infrared and radio wavelengths. Infrared light, with its longer wavelengths, can penetrate dust clouds that are completely opaque to visible light. It's akin to using a heat sensor to find a person hidden behind a wall. The warm glow of a nascent star buried deep within the cold dust can be detected as an infrared signature. Radio waves, which have even longer wavelengths, can pass through the dust almost unimpeded, allowing scientists to map the distribution and motion of the cold molecular gas itself. By combining these views, astronomers can construct a detailed picture of the structures and active processes occurring within the dark lane's inky depths, revealing protostars in their earliest, most embedded stages of formation that would otherwise remain completely invisible. This shadowy river of dust, far from being a simple curtain, is an active and critical component of the nebula's ongoing life cycle, a place where the future of Orion is being written in the dark. While the dark lanes shelter the quiet birth of new stars, at the very heart of the Orion Nebula rages a titan whose influence shapes the entire cosmic landscape. Meet Theta1 Orionis C, the dominant and most massive star within the famed trapezium cluster. This is not merely another bright point of light. It is a stellar behemoth, a searingly hot O-type star whose power is almost beyond human comprehension. To put its brilliance into perspective, Theta1 Orionis C outshines our own Sun by a factor of over 200,000 times, and its surface temperature soars to a blistering 40,000 degrees Celsius. But its raw luminosity is only part of the story. This star is the primary engine, the central power source responsible for making the entire Orion Nebula visible to us across the vast expanse of space. The nebula's iconic glow is not simply reflected starlight. It is a vast fluorescent light show, and Theta1 Orionis C is the ultimate power grid. The star unleashes a torrent of ultraviolet radiation so intense that it violently strips electrons away from the atoms of hydrogen gas that fill the nebula. This process, known as ionization, energizes the gas, causing it to fluoresce with that characteristic ethereal glow we see so clearly in telescopes. In many ways, Theta1 Orionis C is like a colossal cosmic ultraviolet lamp, and the surrounding nebula is the glowing screen it illuminates. Without this star's relentless energy output, the Orion Nebula as we know it, a bright emission nebula, would simply not exist. It would remain a dark, cold cloud of gas, invisible to optical telescopes and hiding its stellar nursery from our view. Yet, for all its power and central role, this stellar monarch exhibits a behavior that has long puzzled astronomers. It is moving. And not just drifting slowly, but racing through its own domain at a surprisingly high velocity, a speed that classifies it as a potential runaway star. This presents a fascinating cosmic contradiction. How can a star so massive, a star that seems to be the anchor of its entire cluster, also be a stellar fugitive speeding through space? The most compelling theory to explain this paradox involves a dramatic gravitational showdown in the star's recent past. The trapezium cluster is a dense, crowded environment, a celestial pool table where massive stars orbit one another in complex, often unstable systems. Astronomers theorize that Theta1 Orionis C was likely once part of a very tight multiple star system, a gravitational tangle of 3 or 4 massive stars orbiting dangerously close to one another. In such a volatile environment, a close gravitational encounter can act like a cosmic slingshot. If one star in the system gets too close to its companions, the complex interplay of gravitational forces can violently fling one of the stars outward at tremendous speed, while the other stars recoil in the opposite direction or merge together. This ejection event would have been a moment of incredible violence, a gravitational explosion that propelled Theta1 Orionis C on its current path. The fact that it remains within the nebula simply suggests this event happened relatively recently on a cosmic timescale. It hasn't had enough time to actually escape the vast cloud it helps illuminate. This theory transforms our view of the nebula's heart from a stable royal court to the scene of a recent chaotic coup, where the reigning king was brutally ejected from his own throne room. The implications of this stellar speedster extend far beyond its own trajectory. Its powerful solar wind, a stream of charged particles flowing from its surface, and its intense radiation pressure are the primary sculpting forces that are actively eroding and dispersing the nebula itself. Over millions of years, the energy from Theta1 Orionis C and its trapezium siblings will ultimately blow away the very gas and dust clouds that gave them birth, effectively dismantling their own nursery and bringing this vibrant chapter of star formation to a close. So, this runaway star is not just a passive resident. It is both the creator of the nebula's magnificent glow and the agent of its eventual destruction, a beautiful and destructive force whose own turbulent history is written in its rapid flight through the cosmic landscape it dominates. While we have been exploring the grand, sweeping forces that shape the Orion Nebula, from the powerful winds of runaway stars to the violent radiation boiling away infant solar systems, there exists a phenomenon on a much smaller yet equally violent scale. Tucked away within the nebula's intricate structure, astronomers have discovered something that seems almost like the aftermath of a cosmic gunfight, the enigmatic Orion Bullets. These are not solid projectiles, but rather incredibly dense, compact clumps of gaseous iron hurtling through space at absolutely staggering speeds, up to 400 kilometers per second. At that velocity, you could travel from the Earth to the Moon in under 20 minutes. Each of these bullets is roughly 10 times the size of our entire solar system, and they are racing outward from the nebula's core, leaving brilliant and perplexing trails in their wake. What makes these objects so visually striking, and the source of their unusual name, is their distinct teardrop or bullet-like shape. As these superheated gas clumps tear through the surrounding, colder nebula material, they don't just slip through quietly. They plow into it, creating a powerful shock wave at their leading edge. This shock front acts like a cosmic plow, compressing and violently heating the ambient hydrogen gas it encounters to temperatures high enough to make it glow with a brilliant, fiery light. This creates the illusion of a luminous tip on each bullet, a shining cap of hot gas that makes the entire structure look eerily like a tracer round fired from some unimaginably large rifle. Behind this glowing tip streams a long, cooler tail of gas, visible only to telescopes that can see in specific wavelengths, marking the bullet's path like a cosmic contrail. The central mystery, of course, is what cosmic cannon could possibly have fired these gargantuan projectiles. What kind of event has enough raw energy to accelerate blobs of gas the size of solar systems to such hypersonic velocities? The most widely accepted theory points to a truly cataclysmic event deep within the obscured heart of the nebula, the explosive birth of a very massive star. The process of star formation is not always a slow, gentle collapse. When a particularly large star forms, the final stages of its creation can be incredibly violent and dynamic. Astronomers propose that around 400 to 1,000 years ago, an event occurred in the dense core of the Orion molecular cloud, hidden from our direct view by thick layers of dust. This event was likely a powerful, asymmetric explosion, perhaps caused by the chaotic interplay of gravitational infall and the sudden ignition of ferocious stellar winds from a newborn stellar giant. In this scenario, the bullets are interpreted as the shrapnel from that stellar explosion. The tremendous, focused energy released in one direction would have acted like a natural particle accelerator, scooping up pockets of enriched gas containing elements like iron that were forged in previous generations of stars, and blasting them out into the surrounding nebula. Their uniform direction, all streaming from a single central point, strongly supports this idea of a single, powerful ejection event. It's as if we are witnessing the lingering echo of a stellar tantrum, a brief but incredibly violent outburst that punctuated the relatively slow and steady process of star formation. The Orion Bullets serve as a stark reminder that the Nursery is not just a place of serene creation. It is also a site of immense, sudden, and directional violence, where the universe itself can act as a marksman, firing colossal projectiles across the light years. Just as the colossal bullets showed us the immense violence of star formation on a grand scale, there exists a far more common but equally spectacular phenomenon that acts as the personal signature of a newborn star finding its voice. These are the Herbig-Haro objects, named after the two astronomers who first studied them in detail. They are not stars themselves, but rather the brilliant, glowing aftermath of stellar tantrums, the powerful jets and shockwaves unleashed by infant suns as they struggle to be born. In the Orion Nebula, some of the most famous and beautifully studied examples, like HH1 and HH2, provide a textbook case of this cosmic process in action, giving us a front-row seat to the turbulent infancy of stars, much like our own sun was billions of years ago. To understand what creates these brilliant knots of light, we need to look at the chaotic environment of a protostar, a star still in the process of gathering mass from its surrounding gas and dust disk. As the star contracts under gravity, it doesn't just pull material in uniformly. The infalling matter gets channeled by the star's nascent magnetic fields, which act like powerful, focused funnels. Much of the material spirals down onto the star's surface, helping it grow, but a significant fraction gets redirected and accelerated outward at nearly supersonic speeds from the star's poles. This results in two powerful, narrow beams of ionized gas shooting out in opposite directions, like cosmic exhaust pipes from a stellar engine. These jets can stretch for trillions of miles, far beyond the confines of their own fledgling solar system. The spectacular glow of a Herbig-Haro object occurs when these supersonic jets violently collide with the slower moving clouds of gas that surround the newborn star. It's a collision of cosmic proportions. When the jet rams into this stationary or slower moving material, it creates a tremendous shock wave, not unlike a sonic boom on an astronomical scale. The gas at the front of this shock is compressed and heated to extreme temperatures, causing it to glow with intense, excited light. We see this as a series of bright, often bow-shaped knots strung out along the jet's path. These knots are not solid objects. They are temporary, luminous hotspots in a continuous flow, marking the places where the star's energetic outflows are plowing into the interstellar medium. The entire structure acts as a brilliant beacon, highlighting a star's frantic efforts to clear away the very cocoon that gave it life. The famous pair HH1 and HH2 offer a perfect illustration of this entire process. They are not two separate objects in the traditional sense, but rather the two opposing ends of a single, vast system. A hidden protostar tucked away in a dense cocoon of dust is firing a bipolar jet. One jet pointed roughly in our direction creates the glowing shocks we call HH1. The opposite jet, shooting away from us into the nebular gas on the other side of the star, creates the shocks we call HH2. We are essentially seeing the two glowing impact points of a single cosmic event, with the central engine hidden from our direct view. This setup allows astronomers to study the symmetry and power of these outflows, providing crucial information about the mass and energy of the star that is still veiled behind its birth cloud. These brilliant but ephemeral structures are far more than just a beautiful light show. They are critical to the star's own development. By ejecting mass and angular momentum, the protostar is able to slow its own spin, preventing it from tearing itself apart during its formative years. Furthermore, these powerful jets help to blow away the remaining gas and dust from around the star, ultimately halting the infall of material and finalizing its mass. In this way, a Herbig-Haro object is a star's definitive birth cry, a violent and necessary process that announces its arrival while simultaneously carving out the space it will one day call home. They are a transient phase in a star's life, lasting only a few tens of thousands of years, a mere blink in cosmic time, making our ability to witness them in the Orion Nebula a rare and precious glimpse into the universal mechanism of stellar birth. Now, as we shift our gaze from the violent, visible outflows of newborn stars to the subtle, invisible light that permeates the entire nebula, we encounter a mystery written in a spectrum our eyes cannot see. Throughout the Orion Nebula, and indeed across much of our galaxy, powerful infrared telescopes have detected a series of faint but distinct emission bands, a kind of cosmic signature that has stubbornly resisted full explanation for decades. These are the unidentified infrared bands, and while the name might sound bureaucratic, the implications of what they could represent are truly profound. This is not a single object you can point a telescope at, but rather a pervasive, ghostly fingerprint that is woven into the very fabric of the nebula's glow, suggesting that something fundamental and widespread is occurring within its clouds. The light from these bands doesn't come from the hot, ionized gas that creates the nebula's famous visible glow, nor from the simple thermal heat of dust grains. Instead, it appears at very specific wavelengths in the infrared part of the spectrum, acting like a barcode that points to a particular type of molecule. For a long time, the leading hypothesis has centered on a fascinating class of complex organic compounds known as polycyclic aromatic hydrocarbons, or PAHs for short. Imagine these not as living organisms, but as the robust, carbon-based skeletons of much larger biological molecules. Structurally, they are like tiny, flat chicken wire sheets or miniature fragments of graphite, made up of rings of carbon atoms with hydrogen atoms attached around the edges. They are thought to form in the cool, outer atmospheres of aging carbon-rich stars and are then expelled into space, where they can become incorporated into clouds like the Orion Nebula. What makes the pH hypothesis so compelling is how these molecules are thought to behave in the nebula's harsh environment. When a pH molecule is floating in space and gets hit by a single photon of ultraviolet light from a massive star like Theta1 Orionis C, it doesn't just get warm, it enters an excited state. To release that absorbed energy, the entire molecule begins to vibrate intensely, like a tiny tuning fork ringing at a specific pitch. It then re-emits that energy as infrared light at very distinct wavelengths, which correspond precisely to the vibrational modes of its carbon-hydrogen bonds. This process effectively turns each pH molecule into a microscopic infrared beacon, and with trillions upon trillions of them spread throughout the nebula, they collectively produce the unidentified infrared bands we detect. Their widespread presence would indicate that the basic, rugged building blocks of organic chemistry are not rare in the cosmos, but are in fact commonplace, scattered liberally across star-forming regions where new planets are being assembled. However, the story is not so simple, and this is where the true scientific mystery deepens. While pHs are a strong contender, the exact match between the observed infrared bands and laboratory spectra of known pHs is not perfect. There are subtle discrepancies, small shifts, and additional features that suggest the material responsible might be something slightly different, perhaps more complex or exotic. Some researchers propose that we might be seeing not pristine pHs, but where the mystery becomes truly fascinating is that some scientists have proposed alternatives that are even more exotic. What if the carriers of these bands are not organic molecules at all, but something entirely different, like a form of amorphous carbon or even nanoparticles of diamonds? Yes, the idea of tiny diamond dust glittering throughout the Orion Nebula has been seriously considered, as certain spectral features can also be reproduced by such materials. This ongoing debate highlights a fundamental challenge in astrochemistry, interpreting the faint light from objects hundreds of light years away. We are essentially trying to identify a substance by the specific color of its glow, but from an immense distance and in an environment we cannot directly sample. The Orion Nebula acts as a vast natural laboratory, and the unidentified infrared bands represent one of its most persistent and important puzzles. Determining their true origin is critical because it directly impacts our understanding of cosmic chemistry. If they are PAHs or similar complex organics, it confirms that the universe is efficient at creating the hardy precursors to life, spreading them through nebulae where they can eventually become part of new planetary systems. If they are something more mineral-like, it would point to a different yet equally important pathway for carbon in space. This unresolved question serves as a powerful reminder that even the most advanced observations can still leave us with profound uncertainties, driving the continued quest to decipher the chemical language of the cosmos. Now, imagine if you could take the chaotic violence of a Herbig-Haro jet and compress its energy into an intensely focused, coherent beam of radiation, a natural laser broadcasting from deep within the nebula. This isn't science fiction, it's the reality of water masers, one of the most precise and peculiar tools nature has given us to probe the hidden cradles of star birth. A maser is an acronym for microwave amplification by stimulated emission of radiation essentially, a laser that operates in the microwave part of the electromagnetic spectrum instead of visible light. And in the turbulent, shocked regions surrounding newly formed stars in Orion, water molecules are coerced into performing this incredible natural feat, acting as cosmic amplifiers that beam out a powerful, narrow signal we can detect from Earth. For a water maser to fire up, a very specific and extreme environment is required. It begins with the presence of warm, dense water vapor, which is common in the dusty disks and violent outflows associated with protostars. But the secret ingredient is a source of intense energy to pump the system typically, the shock wave from a supersonic jet colliding with surrounding gas, exactly like those we see in Herbig-Haro objects. This shock wave does two critical things. First, it violently compresses and heats the gas, releasing and exciting water molecules. Second, it creates a population inversion, a state where more water molecules are artificially boosted into a higher energy level than remain in a lower one. This setup is inherently unstable. When a passing microwave photon of the right FREQUENCY Chinese letter these excited molecules, it triggers a chain reaction, causing them all to drop back down to their lower energy state in perfect sync, releasing a flood of identical photons. This process amplifies the original signal by a staggering factor, resulting in an incredibly bright, narrow beam emission at a specific microwave frequency. What makes these water masers so valuable to astronomers is not just their power, but their extraordinary compactness and the precise information they carry. A maser spot can be astonishingly small, sometimes no larger than our own solar system, which is a tiny pinpoint on the scale of a nebula that spans dozens of light years. Because they are so small and bright, they act like brilliant beacons, allowing scientists to map the structures around newborn stars with a level of detail that is otherwise impossible. By observing how the light from these masers varies over time, and by using a technique called interferometry to pinpoint their exact locations, researchers can trace the high-speed motions of gas within protostellar disks and outflows, measuring velocities and turbulence in these regions with exquisite precision. Each maser spot is like a tiny lit fuse, showing us the exact path of a shock wave as it rips through the stellar nursery. The presence and behavior of water masers in Orion provide a unique window into the most energetic, small-scale dynamics of star formation. They reveal where gas is being accelerated to tremendous speeds in bipolar jets, and they can even be used to measure the distance to the nebula itself with remarkable accuracy through geometric techniques. Observing how these masers flare and fade gives us a real-time look at the episodic nature of mass accretion onto the fledgling star, hinting at bursts of growth followed by periods of relative calm. In essence, these natural lasers are cosmic diagnostics, illuminating the violent, invisible processes that shape a star's earliest moments, proving that even something as simple as a water molecule can become a powerful searchlight, revealing the secrets of cosmic creation. Among the sweeping clouds and glowing arcs of the Orion Nebula, there is one feature that stands out with remarkable clarity: a stark, luminous boundary that cuts across the vista like a celestial shoreline. This is the Orion Bar, a bright, sharply defined ridge that presents one of the most vivid examples in the entire sky of a photodissociation region. To understand what we're seeing here, we need to visualize the nebula not as a static picture, but as a dynamic battlefield where two cosmic forces are in a constant titanic struggle. On one side, you have the immense ultraviolet radiation flooding out from the trapezium stars, particularly Theta1 Orionis C. This radiation is so energetic that it rips electrons from atoms, creating the ionized hydrogen gas that makes the bulk of the nebula glow. But this powerful wave of light does not extend forever. As it travels outward from its source, it eventually slams into the dense, cold wall of the parent molecular cloud, a vast reservoir of gas and dust that has not yet been evaporated by the stellar onslaught. The Orion Bar is the visible edge of that collision, the glowing front line where the unstoppable force of starlight meets the immovable object of cosmic dust. The sharpness of the bar's edge is a direct result of this physics. The ultraviolet light from the massive stars is so intense that it completely ionizes the hydrogen gas in the inner part of the nebula, creating a vast hot plasma known as an H2 region. But as this radiation travels, it is gradually absorbed. By the time it reaches the denser cloud material, its most energetic photons have been used up, and it can no longer fully ionize the gas. Instead, it has just enough energy to break apart or photodissociate molecules like hydrogen, tearing them apart into individual atoms without giving them an electric charge. This transition zone from the fully ionized interior to the cold, neutral molecular cloud is the photodissociation region, and the Orion Bar is its textbook manifestation. The reason it appears so bright and sharp is that we are looking at it almost perfectly edge-on, giving us a cross-sectional view of this incredibly active interface, a glowing front that is only about 500 times the distance from the Sun to Pluto in thickness, razor thin on a cosmic scale. What makes this region far more than just a beautiful boundary is the incredibly complex chemistry it hosts. This thin, irradiated layer acts as a vast natural chemical laboratory, one of the most productive in our galactic neighborhood. The same ultraviolet light that breaks molecules apart also provides the energy to drive new and exotic chemical reactions. In the slightly cooler, dense gas just behind the bright edge, atoms and simple molecules are constantly being smashed together and rearranged by the pervasive radiation. This is where molecular hydrogen can reform on the surfaces of dust grains, and where more complex molecules, including the precursors to organic compounds, can begin to take shape. The conditions within the bar are perfect for creating a rich soup of chemical species, including carbon monoxide, hydroxyl radicals, and various ions that are difficult to produce elsewhere. Astronomers study the specific light signatures or emission lines from these molecules to understand the physical conditions, the density, temperature, and radiation field inside this unique cosmic environment. Its role as a natural laboratory is what makes the Orion bar so invaluable to science, because it is relatively close to Earth and presents such a clear edge on view. It offers an unparalleled opportunity to test our models of how interstellar chemistry works. We can observe how different molecules survive or are destroyed as we move from the intensely irradiated face of the bar into the shielded depths behind it. This allows us to create a detailed chemical map of a photodissociation region, which is a common structure found throughout the universe wherever massive stars influence their surrounding cloud. By decoding the processes at work in the Orion bar, we gain a template for understanding the life cycle of matter in galaxies, from the diffuse gas of the interstellar medium to the molecular clouds that will one day collapse to form new stars and planets. This bright, sharp ridge is more than a scenic feature. It is a fundamental blueprint for one of the universe's most common and chemically fertile environments, a place where the raw ingredients for future worlds are being forged in the fiery border between light and shadow. But the drama of a star's birth doesn't always unfold in the steady, predictable way we might imagine. Sometimes a young star experiences a cataclysmic tantrum so violent and sudden that it completely transforms its identity, becoming a brilliant beacon that can be seen across the galaxy. This brings us to one of the most explosive phenomena in stellar infancy, the Theta1 Orionis star, named after the original prototype discovered in the constellation Orion. These are not mature stars, but young stellar objects that undergo a spectacular and mysterious transformation. In a shockingly short period of time, sometimes just a few months or years, a faint, unassuming protostar can suddenly flare up, increasing its brightness by a factor of 100 or even several hundred times. It's as if a dim light bulb were suddenly swapped for a colossal cosmic searchlight, an event so dramatic it fundamentally changes how the star appears to us. The original star that defined this class, Theta1 Orionis itself, provided the textbook example of this bizarre behavior. Back in 1936, this previously unremarkable star in the Orion molecular cloud complex erupted without warning. It brightened by over 250 times in a matter of a single year, eventually peaking to become a star of notable brightness before slowly, over decades, beginning to fade again. This was not a supernova, the final death blast of a star. The star itself survived. Instead, it was a monumental outburst from a star still in the process of formation, a violent developmental spurt that revealed a previously hidden and energetic phase of stellar youth. While the exact trigger for these events is still a subject of intense research, the leading theory provides a compelling narrative that ties directly into the chaotic environment of a protostar's circumstellar disk. The most widely accepted explanation for these spectacular outbursts points to a massive, unsustainable feeding frenzy. Imagine a young star surrounded by its vast, spinning protoplanetary disk, the same kind of disk we see in the Proplyds. Normally, material from this disk trickles slowly and steadily onto the star's surface in a process called accretion, but theoretical models suggest that this flow can become unstable. The disk can develop a gravitational bottleneck, a region where material backs up like water behind a dam. For decades, matter accumulates in the outer disk, not moving inward, building up tremendous pressure and density. Then something, perhaps a gravitational nudge from a companion star or an instability within the disk itself, causes this dam to break. When this happens, the result is an accretion avalanche of almost unimaginable scale. A colossal wave of gas and dust containing an amount of material equivalent to the entire mass of the planet Jupiter or more comes crashing down from the outer disk onto the surface of the tiny protostar all at once. The physics of this event are staggering, as this enormous amount of material plows into the star's surface at nearly a third of the speed of light. Its incredible kinetic energy is instantly converted into an enormous burst of heat and light. The infalling matter creates a superheated shock front around the star, causing its surface temperature to skyrocket and its luminosity to explode, creating the dramatic brightening we observe. The star doesn't just get a little brighter, it undergoes a total metamorphosis, outshining its previous self so completely that it appears to be a completely different class of object. This theory elegantly explains several key characteristics of FU Orionis stars. The sudden, rapid rise in brightness matches the model of a sudden, catastrophic release of stored disk material. The slower, decades-long decline in brightness that follows represents the tail end of this accretion event, as the last of the excess material slowly drains onto the star and the disk settles back into a quieter state. Furthermore, the spectrum of the star during an outburst changes dramatically, showing features consistent with a hot, rapidly rotating accretion disk that is suddenly processing an immense amount of energy, rather than the cooler, more placid photosphere of the protostar itself. The existence of such violent outbursts has profound implications for our understanding of how stars achieve their final mass. It suggests that a star's growth is not always a slow and steady process, but can be punctuated by these brief, incredibly intense growth spurts. A single FU Orionis outburst might dump enough material onto a star to account for a significant percentage of its entire final mass. For any planets trying to form in that disk, such an event would be apocalyptic. The sudden flooding of the inner disk with intense radiation and heat would violently alter the chemical composition of the disk, vaporizing ices and blowing away lighter gases, fundamentally shaping the architecture of any future planetary system that might emerge from the chaos. While identifying a star actively undergoing such an outburst in the heart of the Orion Nebula is challenging due to the dense crowd of stars, the presence of the original FU Orionis in the broader Orion cloud complex confirms that this dramatic phase of stellar life is a reality, a breathtaking reminder that the birth of a star can be as volatile and explosive as its death. While the Orion Nebula presents a breathtaking picture of stellar birth, there are whispers in its chemical makeup and the motion of its gas that tell a much more violent and ancient story, one of colossal stellar death that occurred long before the trapezium stars ever ignited. This leads us to the enigmatic silent supernova candidates. Unlike the famous Crab Nebula with its bright, expanding shell and a pulsar at its heart, these are cosmic ghost stories, the lingering evidence of massive stars that exploded with unimaginable force but have since vanished, leaving behind no obvious corpse like a neutron star or black hole for us to find. The clues to this ancient cataclysm aren't written in a visible remnant. They are encoded in the very bloodlines of the nebula itself, in the elemental abundances and the high-speed motions of its gas. To understand the evidence, we first need to know what a supernova does to its surroundings. When a truly massive star, many times heavier than our Sun, reaches the end of its life, it doesn't fade quietly. It detonates in a supernova explosion, an event so energetic it can, for a brief moment, outshine an entire galaxy. In that final, furious blast, the star acts as a cosmic forge, creating heavy elements through rapid nuclear fusion. Elements like silicon, sulfur, oxygen, and most tellingly, iron are synthesized in the heart of the explosion and then blasted out into space at tremendous speeds, enriching the surrounding interstellar cloud with this newly forged material. This chemical pollution is a permanent fingerprint, a telltale sign that a previous generation of massive stars lived and died in that location. When astronomers perform a detailed chemical census of the Orion Nebula's gas, they find precisely this kind of enrichment. The abundances of certain elements, particularly iron, are higher than we would expect if the gas had only been processed by the current generation of young stars. It's as if the cosmic soup has been seasoned with ingredients from a much older, more violent recipe. This points compellingly to a prior generation of stars that lived fast, died young, and exploded, seeding the original molecular cloud with the heavy elements that now make up the nebula and the planetary systems forming within it. Our own solar system contains such elements, evidence that we, too, are the children of long-vanished supernova. The second major line of evidence comes from the gas itself. Observations have revealed that some regions of the nebula contain gas that is moving at unexpectedly high velocities, too fast to be explained solely by the stellar winds from the current trapezium stars. These are vast, coherent streams of gas expanding outward as if pushed by a single, powerful, and ancient event. The patterns of this motion are consistent with the aftermath of a supernova blast wave that has since expanded, diluted, and merged with the general turbulent flow of the nebula. We are essentially seeing the faint, lingering echo of a shock wave that has traveled for hundreds of thousands of years, its source long since disappeared from view. So, if a supernova did occur, where is the leftover core? The most fascinating part of this mystery is the conspicuous absence of a visible compact remnant. When a massive star explodes, its core collapses. Depending on its initial mass, this collapse can result in an ultra-dense, rapidly spinning neutron star, a pulsar, or if the core is massive enough, a black hole. A pulsar, with its lighthouse-like beam of radiation, should be a relatively straightforward object to detect if it were pointed toward Earth. Yet, despite extensive searches, no such pulsar has been definitively identified within the Orion Nebula region associated with this ancient explosion. This very absence is paradoxically highly informative. It forces astronomers to consider several compelling possibilities for the fate of the stellar corpse. One scenario is that the supernova explosion was what's known as an asymmetric kick. During the chaotic collapse, the explosion may have been lopsided, rocketing the newly formed neutron star away from its birthplace at hundreds of kilometers per second. This kick velocity could have been so powerful that the neutron star has long since escaped the nebula entirely, traveling far into the interstellar medium, leaving no trace behind. We would be looking at the scene of a crime where the key piece of evidence has fled the scene. Another, even more dramatic possibility is that the progenitor star was so immensely massive that its core collapse did not form a neutron star, but instead created a black hole directly. And not all black holes are easy to find. A stellar mass black hole without a nearby companion star to steal gas from is completely dark and virtually undetectable against the blackness of space. It could be sitting right there in the nebula, a silent, invisible gravitational pit, its presence only betrayed by the ancient chemical pollution and the faint, expanding ripples in the gas that it left behind from its violent birth. This ghostly presence would be the ultimate silent partner in the nebula's history. The implications of a confirmed silent supernova are profound for our understanding of Orion's life cycle. It suggests that the nebula we see today is not the first chapter of star formation in this region, but rather a second or even third act. An earlier cluster of massive stars would have formed, lived out their short lives, and then exploded, their shock waves compressing nearby gas and triggering the collapse that led to the birth of the trapezium cluster and the nebula we see today. This phenomenon, known as triggered star formation, paints a picture of a dynamic, self-regulating ecosystem where stellar death directly paves the way for new stellar life. The silent supernova candidate is therefore not just a ghost of the past. It may very well have been the midwife to the brilliant stellar nursery we admire so much today. Yet alongside these titanic explosions and brilliant jets, there exists a far more subtle and pervasive mystery, one that required us to listen to the universe in an entirely different kind of light to even notice it. Throughout the Orion Nebula and in many other star-forming regions, astronomers have detected a faint, shimmering glow in the microwave portion of the electromagnetic spectrum. This isn't the sharp, coherent signal of a water maser, but a diffuse, widespread background hum that has been dubbed anomalous microwave emission. For years, this signal was a genuine puzzle because it didn't match the expected emission from any known source. It wasn't the thermal radiation from warm dust, and it wasn't the synchrotron radiation from high-energy electrons spiraling in magnetic fields, which are the two usual suspects for microwave light. This was something new, something anomalous, and its explanation points to a bizarre and unexpected behavior of the tiniest components of interstellar dust. To understand the proposed solution, we need to shrink our perspective down to the nanometer scale. Imagine a single, incredibly tiny dust grain, so small it's composed of only a few hundred or thousand atoms. One leading hypothesis suggests that these grains could be nanodiamonds, microscopic crystals of carbon forged in the atmospheres of cool, old stars and then scattered into space. Now picture one of these nanodiamonds floating in the vacuum. It's not a static object, it's constantly being bombarded by photons from starlight and collisions with other atoms. When it absorbs a photon, it doesn't just heat up evenly. Instead, that tiny packet of energy can set the entire grain spinning at an incredible rate, billions or even trillions of rotations per second. It's like flicking a microscopic, asymmetric marble and watching it whirl in place. This furious rotation is the key to the mystery. According to the laws of physics, any rotating object that carries an electric charge will emit electromagnetic radiation. For most large objects, this effect is negligible, but for a nanometer-sized grain spinning at terahertz frequencies, the effect becomes significant. The grain acts like a microscopic radio transmitter, emitting radiation at a frequency directly tied to its rotation speed. For the population of nanodiamonds theorized to exist in the Orion Nebula, the collective spin of countless trillions of these particles would produce a broad, continuous spectrum of emission that peaks right in the microwave range, perfectly matching the observed anomalous signal. In this scenario, the eerie microwave glow isn't a product of heat or magnetic fields, but of the universe's most minuscule spinning tops. The nanodiamond hypothesis, while elegant, is not the only contender in the quest to explain this emission. Another compelling theory involves a different class of dust grain known as polycyclic aromatic hydrocarbons, the same PAHs we encountered with the unidentified infrared bands. These flat, plate-like molecules can also be set spinning by the same physical processes. When they rotate, their irregular shape and distribution of electric charge cause them to emit microwave radiation through the same mechanism, known as electric dipole radiation. So, the scientific debate continues. Is the anomalous microwave emission a testament to spinning diamonds or to whirling organic sheets? The answer likely lies in a complex mixture, where different populations of nanoparticles contribute to the overall signal in varying degrees depending on their specific environment. Unraveling this mystery is far more than an academic exercise. It has profound implications for our understanding of the cosmos itself. Interstellar dust is not just cosmic dirt. It plays a critical role in the formation of stars by helping gas clouds cool and collapse. It provides the surfaces upon which simple molecules like molecular hydrogen can form, and it carries the heavy elements that will one day be incorporated into planets and potentially living organisms. If a significant fraction of this dust is in the form of spinning nanodiamonds or complex organics, it forces us to revise our models of the interstellar medium. It means the cosmic recycling process is even more efficient at creating and distributing these resilient, complex materials than we thought. The presence of nanodiamonds in particular would indicate environments of extreme pressure and temperature are common in the outflows of dying stars, seeding the galaxy with these hardy crystals. This faint microwave whisper, once an unexplained anomaly, is thus a powerful probe into the hidden nanocosmos, revealing a dynamic world where the smallest particles, spinning in the void, collectively broadcast a secret that is only now beginning to be heard. While the visible nebula dazzles us with its glow, the true cosmic factory lies hidden just behind the curtain, in a region so dense and cold that it's completely invisible to our eyes. This is the Orion Molecular Cloud 1 core, often abbreviated as OMC1, and it represents the dark, raw material from which the entire spectacular nebula was forged. Think of the glowing Orion Nebula as the brilliant, illuminated stage of a theater. OMC1 is the massive, bustling backstage area where all the sets, props, and actors are being prepared before the show begins. This core is a vast reservoir of frigid gas and dust, so thick that it blocks all visible light, creating a dark bay adjacent to the nebula's brilliance. It is within this seemingly empty blackness that the most fundamental and strange chemistry in the Orion complex is taking place, a chemistry that may hold the very precursors to life itself. What makes OMC1 so special is its incredible density and frigid temperature. The cloud core is a compact, tumultuous region where the concentration of molecular gas is thousands of times denser than the average of the interstellar medium. This density, combined with temperatures hovering just a few tens of degrees above absolute zero, provides the perfect protected environment for chemistry that would be impossible out in the open, where harsh ultraviolet radiation would instantly break apart delicate molecular structures. Shielded within this cosmic deep freeze, atoms and simple molecules have the time and conditions to collide, stick together, and slowly build up into increasingly complex structures on the surfaces of tiny, icy dust grains that act as miniature chemical laboratories. It is here that radio telescopes have uncovered a veritable soup of organic molecules, turning this dark cloud into one of the richest chemical hotspots known in our galaxy. Astronomers have identified a bewildering array of compounds, including familiar ones like water, carbon monoxide, and ammonia, but also far more complex species. They've found methanol, the simplest alcohol, acting as a fundamental building block. They've detected formaldehyde, acetaldehyde, and even vinyl cyanide. Perhaps most tantalizing of all are the detections of molecules like glycolaldehyde, a simple sugar, and methyl formate, which is related to the molecules that form the backbone of more complex organic structures. This isn't just a random collection of chemicals, it's a coherent chemical system that appears to be following pathways toward greater complexity, crafting the very ingredients that, under the right conditions, could lead to the formation of probiotic molecules, the chemical precursors to the building blocks of life, such as amino acids and nucleobases. The process thought to be responsible for this chemical bounty is both elegant and fascinating. It begins on the cold, icy mantles that coat interstellar dust grains floating within the cloud. Simple atoms like carbon, oxygen, and hydrogen, along with basic molecules, slowly freeze onto these grain surfaces. Once stuck, they aren't static, tunneling through the ice via quantum mechanics or energized by the occasional cosmic ray. These atoms and molecules can skitter across the surface until they meet and react with one another, forming new, more complex molecules. This surface chemistry is incredibly efficient for creating molecules that would have a hard time forming in the gas phase. Then, when a new protostar ignites nearby, or a shock wave from a stellar outflow passes through the region, The slight warmth from this event is enough to evaporate or kick these newly formed complex molecules right off the dust grains and back into the gaseous state. It's as if the cloud is quietly baking a cosmic cake on its dust grains, and a passing shock wave acts as an oven timer, releasing the finished product into the surrounding gas where our telescopes can finally detect it. The immense significance of OMC1 lies in this demonstration that the fundamental chemical groundwork for life is not a rare or special event, but a natural and widespread consequence of star formation. The cloud is a stellar factory not just because it is forming new stars, but because it is simultaneously manufacturing the complex chemical inventory that will be inherited by those new stellar systems. The protoplanetary disks that form around infant stars within this core will already be seeded with this rich soup of organic molecules. When planets eventually coalesce from these disks, they will be born with these prebiotic compounds as part of their very foundation. This suggests that the chemical potential for life could be built into planetary systems from their very inception, a profound idea that places our own origins squarely within a universal process. The Orion molecular cloud one core, a dark and silent void to our eyes, is in reality a humming, sophisticated chemical plant, silently assembling the Lego bricks of the universe in the cold and dark, long before the first star ever shines. But if you thought the explosive tantrum of an FU Orionis star was dramatic, it pales in comparison to the sheer, unbridled chaos of an event that makes stellar outbursts look like a sparkler. Deep within the Orion molecular cloud, hidden from our optical view, lies a region known to astronomers simply as BN/KL, an acronym for the scientists who discovered its infrared and radio signatures, Becklen, Neugebauer, and Kleinman-Low. This is not a serene stellar nursery. It is a cosmic crime scene, the site of a cataclysmic explosion so powerful that it is still unfolding before our eyes, a runaway disintegration of an entire star system that occurred on a cosmic timescale just moments ago. The scale of the violence in the BN/KL region is almost incomprehensible. Imagine an event that released as much energy in a single, brief burst as our sun will radiate over its entire 10 billion-year lifetime. That is the magnitude of the explosion we are witnessing the aftermath of. The evidence is etched across light years of space in the form of a monstrous bipolar outflow. Dozens of enormous clumps of molecular gas, some of them many times the mass of Jupiter, are hurtling outward from a central point at speeds reaching hundreds of kilometers per second. These are not the sleek, focused jets of a Herbig-Haro object. This is shrapnel from a stellar grenade, a vast, messy explosion of gas and dust that has been blasted in all directions, but with a distinct preference for two opposing cones. We are seeing the debris field from a celestial explosion that makes the Orion Bullets look like mere pellets from a shotgun. So, what kind of cosmic event could possibly cause such staggering destruction? The leading theory is as dramatic as the aftermath itself. A stellar billiards game that ended in a catastrophic collision. Astronomers reconstruct the scene like forensic detectives. They believe that just a few centuries ago, perhaps around the time Galileo was first turning his telescope to the heavens, this dense, obscured core of the molecular cloud housed a very compact, very unstable multiple star system. Picture this, 4 or more massive young stars, all gravitationally bound in a chaotic dance within a space smaller than the orbit of Neptune around our Sun. In such a volatile gravitational environment, stability is a fleeting illusion. The stars would have tugged at each other, their orbits decaying and shifting until inevitably, 2 of the most massive stars veered too close together. This close encounter would have been the trigger for total systemic collapse. Instead of a clean gravitational slingshot that might have ejected one star, the 2 approaching stars likely underwent a common envelope event or even a direct collision. This merger would have released an unimaginable torrent of gravitational energy in an instant, effectively detonating the heart of the star system. The sudden, colossal release of energy would have acted like a bomb blast, violently expelling the other stars in the group and shredding any surrounding protoplanetary disks into the high-velocity shrapnel we see today. In this scenario, the BN/KL outflow is the direct result of a stellar merger, a cosmic reboot that tore a family of stars apart and scattered its members across the Orion cloud. The evidence for this stellar breakup is written in the motion of the stars themselves. Radio and infrared observations have been able to track the paths of several key players in this drama, most notably a bright infrared source known as the Becklen-Neugebauer object and a runaway star named Source I. By tracing their movements backward in time, astronomers have made a stunning discovery. Their paths intersect with remarkable precision at a single point in space, and that point corresponds to the very epicenter of the BN/KL explosive outflow. The math shows that approximately 500 years ago, all of these objects were occupying the same tiny volume of space. This is the proverbial smoking gun. It confirms that a single, incredibly violent event in the 15th century launched these stars on their current escape trajectories, flinging them outward while simultaneously blasting the surrounding gas into the spectacular high-speed flow we observe. The repercussions of such an event extend far beyond the immediate drama. This explosive dispersal injects a tremendous amount of turbulence and energy into the surrounding molecular cloud. The shock waves from the outflow can compress nearby gas, potentially triggering the collapse of new pockets of material to form a subsequent generation of stars. It also violently enriches the local environment, spreading the heavy elements that were churned up during the stellar merger. For any nascent planetary systems in the vicinity, an event like this would be an existential threat. Its intense radiation and powerful shocks likely sterilizing or completely disrupting the delicate process of planet formation. The BN/KL region stands as a humbling testament to the fact that star formation is not always a gentle process of collapse, but can be punctuated by these brief, hyper-violent episodes of stellar destruction that reshape their cosmic neighborhood for millennia to come. But to truly see the Orion Nebula as it is, we must first look through a filter, a cosmic curtain hanging between us and its brilliant stage. This is Orion's veil, a vast foreground shroud of cold, neutral hydrogen gas and dust that lies directly in our line of sight, subtly altering and filtering the very light that reaches our telescopes. Imagine looking at a brilliant sunset through a thin, hazy cloud. The colors are softened, the intensity is muted, and certain details are lost. That is the effect of Orion's veil on our view of the nebula. It isn't a part of the main emission region. It's a separate, complex structure that floats in the foreground, and understanding its nature is crucial because everything we observe from Earth has passed through this cosmic lens, meaning the brilliant nebula we think we see is in some ways an interpretation filtered through this enigmatic veil. This veil acts as a gigantic natural spectrometer, revealing its own composition through the way it interacts with the light from the trapezium stars behind it. The hydrogen gas in the veil is neutral, meaning its atoms are intact with their electrons still in place, unlike the ionized hydrogen in the main nebula, which has been stripped of electrons by ultraviolet radiation. When the intense starlight from Theta1 Orionis C and its siblings passes through this neutral gas, the atoms within the veil absorb very specific wavelengths of that light. Each element has its own unique fingerprint, a set of specific colors it will absorb. By analyzing the starlight that makes it through to us, astronomers can see dark, narrow lines in the spectrum where light has been subtracted. These absorption lines are the definitive signature of the veil's presence, allowing scientists to determine not just its chemical makeup, but also its density, temperature, and even its velocity. We know, for instance, that the veil is not a single, uniform sheet, but is composed of multiple layers or filaments, each moving at slightly different speeds, creating a complex, shimmering curtain in front of the cosmic light show. This presents one of the most intriguing puzzles about Orion's veil, its very existence. How can a cloud of cold, neutral hydrogen and delicate dust grains survive so incredibly close to some of the most powerful and destructive stars in our galactic neighborhood? The trapezium stars are pouring out a hurricane of ultraviolet radiation and a relentless stellar wind that should, in theory, have ionized, heated, and blown away this foreground cloud long ago. It's like a delicate sheet of paper managing to remain intact just inches from a blazing blowtorch. The fact that it hasn't been utterly obliterated suggests that the veil is either much more massive and dense than it appears, allowing it to absorb the onslaught without fully disintegrating, or it is being constantly replenished from another source. One compelling theory is that the veil is actually the outer skin of the vast Orion molecular cloud that lies behind the entire nebula complex, a wall of material that is being slowly evaporated by the stellar radiation, with new material continually feeding into it from the protected depths of the molecular cloud, creating a dynamic equilibrium between destruction and replenishment. The structure of the veil is therefore not static. It is a dynamic interface, a battlefront. The side facing the trapezium stars is being constantly heated and ablated, its atoms boiled off into space, while the cooler, shielded side remains relatively intact. This process likely creates a steep ionization front within the veil itself, a transitional zone where neutral gas becomes ionized as the destructive power of the stars gradually eats away at it. The dust grains within the veil add another layer of complexity. These tiny particles are exceptionally efficient at scattering blue light, which is why the veil gives a slight reddish tint to the background nebula, much like our own atmosphere makes the sun appear red at sunset. By studying the precise way this dust polarizes the light passing through it, astronomers can map the magnetic fields that are woven through the veil, fields that may provide a supporting skeleton, adding strength and structure that helps the cloud withstand the tremendous external pressures it faces. Ultimately, Orion's veil is far more than a simple obstacle to our view. It is a crucial component of the nebula's ecology. It serves as a protective barrier for the material that lies behind it, shielding portions of the larger molecular cloud from the full brunt of the ultraviolet assault and potentially allowing new stars to form in its shadow. By absorbing and reprocessing the fierce light of the trapezium, it also contributes to the complex energy balance of the entire region. Decoding its secrets is essential for achieving a true, unobscured understanding of the Orion Nebula's physics. Every measurement we take, every spectrum we record, must be corrected for the veil's filtering effect. It is a reminder that in astronomy, what we see is never the whole story. It is always a view mediated by the intervening cosmos, and in the case of Orion, the most important mediator is this beautiful, complex, and stubbornly persistent shroud of gas and dust. Tucked away within the vast, cold expanse of the Orion molecular cloud, shielded from the destructive ultraviolet glare of the trapezium stars, lies a remarkable and intensely active chemical powerhouse known as the hot core. This is not a region defined by its visible light, but by its radiant heat and complex molecular signature, a tiny, seething crucible that represents one of the most chemically rich environments ever discovered in our galaxy. Imagine a compact zone, only about 1/10 of a light year across, a mere speck on the scale of the nebula, but within that confined space, the conditions are anything but ordinary. The gas here is phenomenally dense, with trillions of molecules packed into every cubic centimeter, and it is warm, with temperatures soaring to over 200 degrees Kelvin, which is positively balmy compared to the near-absolute zero chill of the surrounding molecular cloud. This unique combination of high density and warmth creates a protected chemical laboratory, an incubator where the simple ingredients of the interstellar medium are being forged into the complex organic compounds that could one day seed entire planetary systems with the chemical potential for life. The stark contrast between the hot core and its surroundings is a story of cosmic evolution. the entire region was once a cold, uniform part of the larger molecular cloud. Then a massive protostar began to form deep within its heart. As this nascent stellar giant collapsed under its own gravity, it released a tremendous amount of energy, not as light but as heat, warming the dense cocoon of gas and dust immediately surrounding it. This was the genesis of the hot core. The rising temperatures triggered a profound transformation. For millions of years, the icy mantles coating interstellar dust grains had been acting as cold storage, accumulating a frost of simple molecules like water, carbon monoxide, ammonia, and methanol. When the core warmed, these icy warehouses underwent a dramatic thaw. The ices sublimated, turning directly from solid ice into gas, and in doing so, they released their entire inventory of frozen molecules back into the surrounding space all at once. This sudden, massive injection of material into the gas phase is what fundamentally altered the region's chemistry, creating the incredibly rich molecular soup we detect today. It is this evaporative event that allows the hot core to act as a brilliant cosmic beacon for radio astronomers. The complex molecules now floating freely in the warm gas have a unique ability to absorb and emit radiation at very specific radio frequencies. Each molecule has its own distinct rotational signature, a set of spectral lines as unique as a human fingerprint. Telescopes tuned to these frequencies can therefore conduct a precise chemical census of the core, and the results are nothing short of astonishing. The list of detected compounds reads like the inventory of an industrial chemical plant. Beyond the simple ices, astronomers have identified a wealth of complex organic molecules, including vast quantities of methanol, a fundamental building block for more complex chemistry. They found methyl cyanide, a molecule with a carbon-nitrogen bond that is of particular interest in probiotic chemistry. Perhaps even more significantly, they have detected dimethyl ether and vinyl cyanide, molecules that are considered direct stepping stones toward the formation of even larger and more complex species, including potential precursors to amino acids and the components of genetic material. This rich chemical diversity doesn't just appear, it is actively manufactured through a sophisticated two-stage process. The first stage occurs in the deep freeze of the pre-stellar cloud on the surfaces of the dust grains. In that frigid environment, simple atoms and molecules that stick to the icy grains can slowly migrate and react with one another, building up more complex structures like methanol in the solid state. This is a slow, patient accumulation. The second explosive stage is the heating event itself. When the ices evaporate, they don't just release their stored molecules, they also unleash them into a warm, dense gas where a whole new world of chemical reactions becomes possible. In this energized environment, the newly liberated molecules collide with one another frequently, and with enough energy to form even larger and more intricate structures through gas phase reactions. The hot core is thus the culmination of both slow, solid-state preparation and rapid gas phase assembly, a one-two punch of chemical synthesis that efficiently produces complexity. The ultimate significance of the Orion hot core extends far beyond its own fascinating chemistry. It provides a powerful model for how the raw ingredients for life might be delivered to infant worlds. When the massive protostar at the center of this core finally ignites and begins to blow away its natal cocoon, the complex molecules synthesized within the hot core will be dispersed into the wider nebula. They will become part of the general reservoir of material from which new, smaller stars and their surrounding protoplanetary disks will form. This means that by the time a rocky planet like Earth begins to coalesce in such an environment, its foundational material is already preloaded with a rich inventory of organic compounds. The water for its oceans and the complex molecules that could jumpstart the chemistry of life may not have to form on the planet itself, but could be inherited directly from the molecular cloud, a gift from a hot core like the one in Orion. This profound connection suggests that the chemical pathways to life's building blocks are not a rare or special occurrence, but a natural and perhaps universal consequence of the star formation process itself, making regions like the Orion hot core not just chemical curiosities, but potential cradles for cosmic life. Soaring above the nebula landscape, like a range of colossal, petrified sequoias carved from luminous mist, are the breathtaking structures known as the Mystic Mountain. Immortalized by the Hubble Space Telescope, these are not solid formations but vast, transient pillars of gas and dust, cosmic butts standing defiantly against an erosive tide of energy. Their dramatic, sculpted forms tell a story of both immense destructive power and the resilient, sheltered pockets of creation that such destruction can inadvertently foster. To understand these pillars is to witness the duality of the nebula itself, where the very forces that tear down the old are simultaneously laying the groundwork for the new. The primary artist responsible for this breathtaking sculpture is the same relentless force that illuminates the entire nebula and defines the Orion bar, the intense ultraviolet radiation from the trapezium stars. This radiation acts like a cosmic sandblaster, but on a scale almost beyond comprehension. As this energetic wind flows outward, it encounters regions of the molecular cloud that are slightly denser and more compact than their surroundings. While the lower density gas is quickly heated, ionized, and blown away, these denser knots can resist the onslaught, at least for a time. The result is a process of differential erosion. The less dense material is scoured away, while the denser pockets are left standing, revealed as towering pillars that seem to point back toward the source of their own destruction. The distinct, finger-like shapes we see are essentially the long shadows cast by these dense cores, with the evaporating gas streaming away from their sides, giving them their characteristic ragged, columnar appearance. Adding to this sculpting force is the physical pressure of the stellar wind itself, a relentless stream of charged particles flowing from the massive stars. This wind physically pushes against the gas and dust, compressing the pillars further and helping to carve out the intricate ridges and valleys that make structures like the Mystic Mountain so visually complex. At the very tips of the pillars, this combined assault is particularly fierce. Here, the pressure from the radiation and wind can become so intense that it triggers a process similar to what we saw in the Proplyds, called photoevaporation. Giant glowing caps of ionized gas form at the pillars' heads, where the external radiation is boiling the material away, and these caps are often seen streaming away as long, wispy tails, making the pillars look like celestial comets frozen in place. Yet within these seemingly doomed structures lies their greatest secret. The very density that allows these pillars to withstand the erosive forces also makes them perfect incubators for the next generation of stars. The immense pressure from the outside is actually helping to trigger star birth within the pillars' shielded hearts. As the external radiation and winds compress the gas and dust, they increase the internal density and gravity to a critical point, causing clumps within the pillar to collapse under their own weight. Deep inside these dark, dusty columns, new protostars are igniting, hidden completely from our optical view. They are cocooned within the same material that protects them from the very radiation that helped create them. To confirm this incredible act of cosmic hide and seek, astronomers must once again look with different eyes. Optical images from Hubble show us the magnificent, sculpted outer shells of the Mystic Mountain, the parts being actively destroyed. But when we switch to an infrared view, the mountain transforms. The dust that is opaque to visible light becomes almost transparent to longer infrared wavelengths. What was a dark, imposing pillar in an optical image suddenly glows with the intense, warm light of nascent stars buried within its core. The infrared view reveals bright, young stellar objects shining from inside the pillar's tip, confirming that the erosion process is not merely destructive. It is also a midwife, catalyzing the birth of stars even as it dismantles their nursery. These pillars are therefore not permanent monuments. They are fleeting, dynamic structures in a constant state of flux. They may stand for only a few 100,000 years, a mere moment in cosmic time before the unrelenting forces from the trapezium stars finally erode them completely, exposing the fledgling stars they sheltered to the harsh environment of the open nebula. The Mystic Mountain and structures like it represent a critical transitional phase in the star formation process. They are the last bastions of the cold molecular cloud, being simultaneously eroded by the brilliant light of the first generation of stars even as they give birth to the next. In their majestic forms, we see the entire life cycle of a stellar nursery written in gas and dust, a beautiful and poignant reminder that in the cosmos, creation and destruction are often two sides of the same celestial coin. Now, let's step back from the individual features and view the Orion Nebula in its entirety, not as a static collection of stars and gas, but as a single, seething metropolis of stellar activity. At its core lies the true engine of this cosmic city, the Orion Nebula cluster, a dazzling and densely packed community of several thousand young stars, all swarming together in a space that is, astronomically speaking, incredibly cramped. To visualize this, imagine taking all the stars that normally occupy a cube of space 1,000 light years on a side and cramming them into a region just 20 light years across. This isn't a serene congregation. It's a gravitational mosh pit, a chaotic and dynamic environment where the simple, orderly orbits we associate with our own placid solar neighborhood are an impossible dream. The gravitational pull from so many stars in such close quarters creates a constantly shifting tidal force field, a reality where a star's nearest neighbors are not fixed landmarks but temporary partners in a frenetic, whirling dance. Within this stellar swarm, one of the most common and impactful events is the close stellar flyby. In our solar system, we take for granted the vast, empty space between our sun and the next nearest star. But in the heart of the Orion Nebula cluster, stars can pass within a few hundred astronomical units of each other, a distance comparable to the outer reaches of our own solar system's Kuiper belt. When a star swings this close to another star that is still surrounded by its protoplanetary disk, the consequences are nothing short of catastrophic for any potential planets. The intruding star's gravity acts like a colossal tidal hand, reaching into the disk and violently disrupting it. It can warp the disk out of shape, strip away its outer layers of gas and dust, and even trigger spiral density waves that either kick developing planetesimals out into the void or send them careening inward toward their parent star. A single, close gravitational encounter can completely rewrite the blueprint for an entire solar system in a matter of a few thousand years. The chaos doesn't stop with mere disruption. These frequent gravitational interactions are also the primary mechanism for ejecting stars from the cluster entirely, creating the runaway stars we've discussed earlier. The process is a cosmic version of a slingshot. When two stars in a binary system have a close encounter with a third, more massive star, the complex three-body gravitational interaction can transfer a tremendous amount of energy. One of the stars, often the least massive of the trio, can be flung outward at high speed, expelled from the cluster core to spend the rest of its life racing alone through the galaxy. Meanwhile, the remaining two stars might recoil from the event, often forming a tighter binary system or even merging. This relentless gravitational pruning is why we see stars like Theta1 Orionis C moving at high velocities, and it's a process that fundamentally shapes the cluster's future, gradually ejecting its lower mass members and leaving behind a more tightly bound core of heftier stars. This violent environment has profound and sobering implications for the search for habitable worlds. While the Orion Nebula cluster is a prolific factory for stars, the very conditions that create them are exceptionally hostile to the long-term stability of planetary systems, especially those in the habitable zone where liquid water could exist. A planetary system forming here faces a gauntlet of threats. First, the intense ultraviolet radiation from massive stars can photoevaporate protoplanetary disks, stripping them of the gas needed to form giant planets like Jupiter. Second, the frequent stellar flybys can truncate disks, robbing them of the raw material in their outer regions, and can destabilize the orbits of any planets that do manage to form, sending them into chaotic, eccentric paths or ejecting them entirely. A planet that might have once enjoyed a stable, circular orbit in the habitable zone could be flung into a deep freeze or a scorching plunge toward its star by a single, random stellar passage. This leads to a fascinating astronomical concept, the rare Earth hypothesis, but on a galactic scale. While the basic ingredients for planets, gas, dust, and complex organics, are clearly abundant in nurseries like Orion, the specific conditions required for a planetary system to remain stable for billions of years, long enough for life to arise and evolve, may be far less common. The serene isolation of our own solar system, which has allowed Earth to remain in a stable, life-nurturing orbit for over 4 billion years, might be the exception rather than the rule. Planetary systems that form in dense, chaotic clusters like Orion may be stillborn, their planetary architectures shattered by gravitational turbulence before they ever have a chance to mature. This suggests that the vast majority of planets in the universe could be rogue worlds, ejected from their solar systems to wander the cold, dark interstellar void, or they could be part of unstable systems where cataclysmic orbital shifts are the norm. The brilliant, crowded core of the Orion Nebula cluster, for all its beauty, may ultimately be a place where the dream of widespread, complex life faces its greatest cosmic challenge, making our own quiet corner of the galaxy seem all the more precious and rare. Now, let's delve into a phenomenon that sounds like it belongs in a book of cosmic laws rather than an astronomy lesson, the so-called forbidden line emissions. When astronomers first pointed their spectroscopes at the Orion Nebula, they saw the expected rainbow of colors, but they also spotted very specific, sharp, and bright lines at certain wavelengths that they could not immediately identify. These were spectral lines that, according to the well-established rules of quantum mechanics as tested in laboratories on Earth, simply should not exist. They were, for all intents and purposes, forbidden. The most prominent of these mysterious lines came from ions of oxygen and nitrogen that had lost 1 or 2 electrons. The puzzle wasn't that these elements were there, it was that they were glowing in a way that physics said was impossible under normal earthly conditions. This was a classic case of the universe presenting a paradox, and the resolution to this mystery would reveal just how truly alien the environment of a nebula can be. The key to understanding this quantum conundrum lies in the bizarre environment of deep space, specifically its incredible emptiness. On Earth, when we excite a gas in a lab, say, by running an electric current through it, the atoms and ions within it get energized. Their electrons jump to higher energy levels. When those electrons fall back down, they emit photons of light at very specific wavelengths, creating the emission lines we see in a spectrum. However, for certain exotic transitions, the quantum mechanical rules state that the probability of an electron taking that particular path back to its ground state is incredibly, vanishingly small. It's considered a forbidden transition because in a laboratory on Earth, it's almost never observed. The reason is our dense atmosphere. In a lab, an excited ion will collide with another atom or molecule 1 billion trillion times per second. Long before it has even a fleeting chance to undergo its slow, forbidden transition, a collision will knock the electron down a different, faster path, robbing it of the opportunity to emit that forbidden photon. But the interior of the Orion Nebula is a vacuum far more perfect than any we can create on our planet. The density of gas there is about 1 atom per cubic centimeter. To put that in perspective, the air we breathe has about 25 billion molecules in the same tiny space. In the nebula, an excited ion of oxygen or nitrogen might float alone for tens of thousands of seconds or even longer before it experiences a collision. This gives it all the time in the universe, quite literally, to finally undergo that slow, statistically improbable, forbidden transition. It's as if the ion is waiting in a vast, empty room for a single, specific, and very slow-moving event to occur, and in the profound quiet it almost always does. The forbidden lines are therefore not breaking any laws of physics. They are simply a testament to the fact that the nebula provides a unique environment where the rarest of quantum processes are given the time and space to become commonplace, painting their signature across the nebula's spectrum. This understanding transformed these spectral lines from a curiosity into one of the most powerful diagnostic tools in all of astrophysics, because the strength of these forbidden lines depends critically on the density of the surrounding gas. They act as a natural cosmic density probe. If the gas were as dense as in our labs, the forbidden lines would be exceedingly weak or absent. The fact that they are so strong and bright in the Orion Nebula's spectrum is direct quantitative proof of its extremely low density. Astronomers can even use the relative intensities of different forbidden lines from the same element to calculate the density with remarkable precision. It's like having a built-in gauge that reads out the emptiness of space itself. Furthermore, the exact wavelength of these lines is subtly influenced by the temperature of the gas. By carefully measuring these shifts, scientists can determine whether a particular filament of the nebula is at 10,000 degrees or 20,000 degrees, providing a detailed thermal map of the entire glowing structure. These forbidden emissions, once a confusing anomaly, are now the very language we use to read the physical state of the nebula, allowing us to understand its pressure, its temperature, and the immense forces that are shaping it from within. For centuries, skywatchers looking up at the familiar constellation of Orion have seen a distinctive feature hanging from the Hunter's Belt, a faint, hazy line of stars known as Orion Sword. To the naked eye, it appears as a soft, glowing patch, a subtle smudge of light that stands in beautiful contrast to the sharp, brilliant points of the belt stars above it. This celestial landmark has captivated human imagination since ancient times, but what we perceive as a simple blur is in fact one of the most profound illusions in the night sky. That gentle glow is not a single star, nor is it a defect in our vision. It is our unaided glimpse of the magnificent Orion Nebula itself, a stellar nursery over 1,000 light-years away, its collective light merged into a single ethereal beacon. The fuzzy patch is the combined radiance of the entire cosmic metropolis. We've been exploring the glowing gas of the nebula, the intense light of the trapezium cluster at its heart, and the countless other stars embedded within it, all blending together into that iconic, mysterious smear. The realization that this was more than just a star was a pivotal moment in astronomical history. In the early 1600s, the French lawyer and astronomer Nicolas Claude Fabry de Peiresc is often credited as the first person to point a telescope at this nebulous spot and note that it was not a star but a diffuse cloud. Just a few years later, the Dutch astronomer Christian Huygens produced a detailed sketch of the nebula, clearly depicting its luminous shape and the tight grouping of stars within it that we now call the trapezium. This was a monumental shift in human understanding. For all of prior history, the sword was simply a part of the constellation's picture, a decorative element in the celestial artwork. With a telescope, it transformed into a place, a specific location in space with its own complex structure. The illusion was broken, revealing that the universe contained objects of an entirely new class, vast clouds of luminous gas where new suns were being born. This single observation helped shatter the ancient Aristotelian notion of a perfect, unchanging heavens and opened the door to the modern study of astrophysics. The primary source of the sword's visible glow is a stunning combination of two distinct phenomena. The most prominent contributor is the nebula's fluorescent gas. As we've learned, the intense ultraviolet light from the massive trapezium stars, especially Theta1 Orionis C, ionizes the vast sea of surrounding hydrogen, causing it to glow with a characteristic reddish-pink light that, while too faint for our color vision to perceive at night, combines into the soft, white haze we see. Superimposed on this glowing canvas is the direct starlight from the trapezium cluster itself. To the naked eye, the four brightest stars of the trapezium, Theta1 Orionis A, B, C, and D, blend together into a single, unresolved point of light. Their combined brilliance, set against the backdrop of the nebula, is what creates the core of the Sword's brightest region. It is this partnership between the concentrated power of young, massive stars and the vast, illuminated cloud they have carved out that creates the iconic visual effect we recognize from our backyards. The historical and cultural interpretations of this celestial feature are as rich and varied as the cultures that observed it. In many ancient traditions, the fuzzy patch was simply accepted as part of the sword, a divine weapon wielded by the great hunter. Some indigenous Australian groups saw the entire Orion region as a canoe, with the nebula representing a group of fishermen sitting within it. Perhaps one of the most poignant perspectives comes from the Maya, who saw great significance in the cosmic haze. They referred to the nebula as a sacred hearth, its glowing embers symbolizing the cosmic fire of creation. This interpretation is strikingly prescient, as modern science has confirmed that the Orion Nebula is indeed a cosmic furnace, a place where the fire of new stars is igniting. It's a beautiful example of how human intuition, guided by careful observation of the heavens, could arrive at a fundamental truth long before the technology existed to prove it. The Orion Sword illusion thus serves as a bridge connecting our ancient, naked eye wonder with our modern, instrument-driven understanding, reminding us that the universe has always been offering its secrets to those who take the time to look up and ponder the mysterious glow in the hunter's blade. Scattered like drifting islands of shadow against the brilliant canvas of the Orion Nebula, you can find small, intensely dark patches that seem to swallow the light around them. These are not the vast, winding rivers of dust like the Great Dark Lane, but something far more compact and isolated cosmic tadpoles of gas and dust known as Bok globules. Named after the astronomer Bart Bok, who championed their study, these globules are among the most simple and pristine objects in the cosmos. They appear as nearly perfect spheres of darkness, so dense and thick with cosmic so that they completely block the light from the glowing nebula or background stars behind them, standing out as stark, black silhouettes against the celestial fire. But within their in-kai, silent hearts, a profound mystery brews, the potential for a star to be born in absolute solitude, far from the chaotic violence of the nebula's core. What makes a Bok globule so fascinating is its stark simplicity and isolation. Unlike the complex pillars and ridges being sculpted by external radiation, a typical Bok globule is a self-contained universe. It's a compact cloud of molecular gas and dust, usually less than a light year across, with a mass ranging from a few times that of our Sun down to the mass of a large planet. Because they are so dense, their interiors are incredibly well shielded from the harsh ultraviolet radiation that floods the rest of the nebula. This creates a deep freeze environment, with temperatures hovering just a few degrees above absolute zero. Within this cold, dark cocoon, the internal pressure is remarkably low, and for a long time, the globule can simply exist, held in a fragile balance between the inward pull of its own gravity and the weak outward pressure of its cold gas. It is a system in suspended animation, a cosmic seed waiting for a signal to sprout. This leads directly to the central puzzle surrounding these dark specks. What exactly provides that signal? What trigger is powerful enough to upset this delicate balance and initiate the gravitational collapse that will eventually lead to the birth of a star? Astronomers have been investigating several compelling catalysts, each one a potential key to unlocking these stellar wombs. One of the most prominent theories involves the immense shock waves that periodically ripple through the nebula. We've already seen the titanic forces at play, the explosive outflow from the BN/KL region, the powerful stellar winds from massive stars, and the distant echoes of ancient supernova. When one of these colossal pressure waves slams into a dormant Bok globule, it acts like a cosmic fist, violently compressing the gas. This sudden increase in density can be enough to push the cloud over the critical threshold, overwhelming the meager internal pressure and allowing gravity to take over, initiating a runaway collapse in the cloud's core. Another potential trigger hits much closer to home, originating from within the globule itself. Even in the deep cold, the globule is not completely static. It is subtly turbulent with internal motions and slight density fluctuations. Sometimes a random, chaotic swirl of gas can create a localized knot that is just dense enough to become gravitationally unstable. This knot begins to pull in surrounding material, growing in mass and gravitational pull until it becomes the dominant center of collapse for the entire globule. It's a process of gravitational seeding where a tiny, random imperfection snowballs into the genesis of a star. A third, more external trigger could be the gentle but persistent pressure of the surrounding hot gas in the nebula. Even without a cataclysmic shock wave, the ambient pressure from the ionized plasma outside the globule can slowly squeeze it, like a hand gradually tightening around a stress ball, increasing its internal density over millions of years until it can no longer support itself against its own weight. To peer into these dark nurseries and witness the earliest stages of this collapse, astronomers must once again turn to the penetrating power of infrared and radio telescopes. While a Bok globule is a perfect void in visible light, it becomes a vibrant and dynamic object at longer wavelengths. Infrared observations can detect the faint warmth of a nascent protostar buried deep within the cold dust, a telltale sign that collapse has begun. Radio telescopes, particularly those tuned to the frequencies of molecules like carbon monoxide and ammonia, can map the internal structure and motions of the gas itself. By studying the subtle shifts in the wavelength of this molecular light, scientists can detect the infall of material, the surest sign that gravity has won and a star is in the process of being built. They can measure the rotation of the globule and even identify the dense, compact cores where single stars or small multiple systems are likely to form. The stellar offspring of a Bok globule are typically quite different from the brilliant giants being born in the trapezium cluster. The relatively small mass of these isolated clouds means they are perfect factories for creating low-mass stars, stars very much like our own sun. This is a profoundly important connection, as it suggests that solitary, sun-like stars may often form in these quiet, dark nurseries, away from the disruptive gravitational pull of their massive siblings. But there's another, even more intriguing possibility. If a Bok globule is particularly low in mass, its collapse might not muster enough material to ignite the sustained nuclear fusion that defines a true star. Instead, it could form a brown dwarf, a mysterious object that straddles the line between planet and star. Brown dwarfs are often called failed stars. They glow with a dull, residual heat from their formation, but are not massive enough to fuse hydrogen in their cores. Bok globules provide one of the leading formation pathways for these enigmatic dark orbs, which may be one of the most common yet hidden populations in our galaxy. The existence and behavior of Bok globules complete a crucial piece of the star formation puzzle in Orion and across the universe. They demonstrate that the birth of stars is not a process confined solely to grand, centralized clusters. It is a versatile and widespread phenomenon that can occur in small, isolated pockets in quiet, dark corners far from the spotlight. These drifting black spheres are the universe's way of ensuring that star formation can proceed on multiple fronts simultaneously, creating both the brilliant, short-lived giants that light up nebulae and the stable, long-lived, sun-like stars that can potentially host planetary systems for billions of years. Each one is a testament to the idea that even in the deepest darkness, the potential for light and new worlds persists, a silent promise of creation hidden within the smallest shadows of the cosmos. This brings us to a cosmic detective story written not in glowing gas, but in the very ages of the stars themselves, a mystery that challenges the fundamental picture of a nebula born in a single glorious burst. When astronomers began to carefully census the population of the Orion Nebula cluster, they made a discovery that seemed to defy logic. The stars were not all the same age. While the brilliant, massive trapezium stars are veritable newborns, just a few 100,000 years old, a blink of an eye in cosmic terms, scattered among them are stars that appear to be several million years older. This isn't a minor discrepancy, it's a glaring age gap suggesting that star formation in this region has been a start and stop process, a series of distinct bursts spread across millions of years. This age paradox forces us to abandon the simple idea of a single, co-eval stellar brood and confront a far more complex and protracted history of creation. The standard model for a stellar nursery was once quite straightforward. A massive, cold molecular cloud collapses under its own gravity, fragments into dense cores, and all the stars within that cloud ignite within a relatively short period of time, perhaps a million years or so. They are, for all intents and purposes, siblings born from the same parent cloud in the same cosmic generation. Orion, however, tells a different story. Here, the evidence points to multiple, distinct generations of stars. The older stars, found both within the cluster and in its wider vicinity, act like celestial fossils, relics of an earlier wave of star formation that occurred long before the trapezium cluster ever began to shine. This means the nebula we see today is not the first act, but likely the second or even third chapter in a long-running saga of stellar birth in this part of space. So, what could cause this episodic process? The most compelling explanation involves a concept known as triggered star formation. Imagine the older generation of stars, the ones that formed several million years ago. Many of these would have been massive stars themselves, living fast and dying young. At the end of their short lives, they would have exploded as supernova. The blast wave from such an explosion is a titanic force that ripples through the surrounding molecular cloud for light years. When this powerful shock front encounters a quiescent, dense pocket of gas, it doesn't just destroy, it also creates. The wave violently compresses the gas, increasing its density to the point where gravity can overcome internal pressure and initiate a new round of collapse. In this scenario, the death of the first generation of stars literally triggered the birth of the second, including the brilliant trapezium cluster we see today. We are witnessing the cosmic legacy of stellar death giving birth to new life, but supernova aren't the only potential trigger. Another powerful mechanism involves the steady, immense pressure exerted by the stellar winds and radiation from massive stars even while they are still alive. This is a slower, more persistent form of triggering. As the first generation of massive stars began to shine, their intense ultraviolet radiation and powerful winds would have begun to carve out vast bubbles in the molecular cloud, creating expanding shells of dense gas on their peripheries. Just as we saw with the pillars of creation, this compression can squeeze pre-existing clumps within the cloud, nudging them over the brink of gravitational collapse. This process, often called radiation-driven implosion, can initiate star formation in a more distributed and sequential manner around the edges of the newly cleared cavity, leading to stars of slightly different ages scattered around the central, youngest cluster. The nebula becomes a dynamic ecosystem where the products of one round of star formation actively engineer the conditions for the next. The implications of this multi-generational model are profound, forcing a complete rethink of how we view stellar nurseries. It transforms the Orion Nebula from a simple snapshot of a single event into a rich, layered history book. The region is not a monolithic entity but a complex stellar population, a mixture of old and new stars whose ages tell a story of successive waves of creation, each potentially triggered by the violent demise or powerful influence of the generation that came before. This protracted history also has direct consequences for the planetary systems forming there. A planet forming around a star in the second generation would be born into an environment already polluted with heavy elements from the supernova of the first generation. This means its raw materials would be richer in elements like iron, silicon, and oxygen, the very elements that make up rocky planets like our Earth. Our own solar system contains such enriched material, suggesting that we, too, may be the products of a multi-generational star formation process, our origins rooted in the death of ancient stars that lived and died in a cluster much like Orion, long before our Sun was even a glimmer in a cosmic cloud. Moving beyond the visible spectrum reveals a far more violent and energetic dimension to the Orion Nebula, one where the very space between the stars is filled with a seething, invisible ocean of million-degree plasma. These are the X-ray superbubbles, vast cavities of incredibly hot gas that envelop the entire nebula complex, glowing not with visible light but with the high-energy punch of X-rays. Their discovery was a revelation made possible only by space-based observatories like the Chandra X-ray Observatory, which can see this fiercely energetic light that is completely blocked by our atmosphere. While optical telescopes show us the beautiful fluorescent glow of the nebula, the X-ray view unveils the colossal, explosive forces that are actively constructing and reshaping this cosmic landscape on its grandest scale. These superbubbles are the direct imprint of the most powerful events in the nebula's history, the accumulating breath of stellar giants and the fading echoes of their cataclysmic deaths. The origin of these immense hot cavities lies in the combined, relentless output of the nebula's most massive stars. Imagine the cumulative effect of the powerful stellar winds we've seen from stars like Theta1 Orionis C, but multiplied across dozens of such stellar behemoths and sustained over hundreds of thousands of years. Each of these stars is essentially a cosmic jet engine, expelling a hurricane of charged particles at speeds of several thousand kilometers per second. Individually, these winds carve out smaller cavities around each star, but collectively, as they expand and merge, they act like a coordinated team of cosmic bulldozers, pushing aside the cooler, denser gas of the molecular cloud and combining their energy to inflate a single, gigantic bubble of low-density, superheated gas. This process, known as mechanical feedback, is the primary engine for creating these X-ray emitting structures, a clear demonstration of how stars can dramatically alter their own birth environment. However, stellar winds alone may not be sufficient to account for the tremendous temperatures and vast sizes of the observed superbubbles. This is where the ghostly signatures of ancient supernova, the silent supernova candidates we discussed earlier, re-enter the narrative with explosive force. When a massive star ends its life in a supernova, the blast wave is an event of almost unimaginable power, injecting energy equivalent to the Sun's total lifetime output in a single, shattering instant. The expanding shock wave from such an explosion heats the surrounding gas to temperatures of tens of millions of degrees and drives it outward at phenomenal speeds, contributing a massive, sudden injection of energy and hot gas to the growing superbubble. It is likely that a combination of these two processes, the continuous, powerful pressure of stellar winds and the periodic, violent blasts from supernova, have worked in concert over the last several million years to inflate the magnificent X-ray structures we observe today, creating a complex, layered fossil record of the region's most energetic events. The gas within these superbubbles exists in a state that is difficult to comprehend. With temperatures soaring to over 1 million degrees Celsius, the atoms within this plasma are moving at frantic speeds and have been stripped of most of their electrons through violent collisions. It is this intensely hot, thin, and ionized gas that produces the diffuse X-ray glow that Chandra detects. The process is different from the nebula's visible light. In the hot bubbles, the X-rays are generated primarily through a mechanism called thermal Bremsstrahlung, which translates from German as breaking radiation. As free electrons, ripped from their atoms, whip past the positively charged atomic nuclei in this ultra-hot soup, they are deflected and slowed by the intense electric attraction. This rapid deceleration causes them to shed energy in the form of X-ray photons, creating the faint, pervasive glow that maps out the colossal cavities. The presence and behavior of these superbubbles are not merely a spectacular side effect. They are one of the most dominant forces governing the large-scale evolution and ultimate fate of the entire Orion complex. These hot, high-pressure cavities act as powerful regulatory mechanisms. By relentlessly expanding, they compress the surrounding cold, dense molecular gas into sheets and filaments, and this compression can trigger the collapse of new star-forming clumps, effectively propagating star formation outward from the center of the bubble in a sequential wave. This is triggered star formation on an epic scale, where the death of one generation of stars directly initiates the birth of the next in the surrounding cloud layers. The superbubbles are the primary agents responsible for shredding and dispersing the parent molecular cloud. Over millions of years, the combined pressure from the hot gas inside the bubbles and the powerful stellar winds will continue to push outward, eventually breaking through the cloud's confines and blowing the remaining gas and dust away into interstellar space. This process will bring the current, vibrant chapter of star formation in the Orion Nebula to a definitive close, leaving behind a naked, open cluster of stars. The X-ray superbubbles, invisible to our eyes but fundamental in their power, are the great architects and destroyers of the nebula, shaping its present structure while simultaneously writing the final act of its cosmic story. Woven through the entire tapestry of the Orion Nebula, invisible to our telescopes yet fundamental to its very structure, is a complex and pervasive network of magnetic fields. These are not the simple bar magnet fields you might remember from school, but a dynamic, tangled web of force that acts as a cosmic puppet master, guiding the flow of gas, shaping the birth of stars, and sculpting the nebula's most intricate features into being. While we cannot see magnetic fields directly, their influence is written everywhere in the nebula's form, from the vast, sweeping arcs of the bow shocks to the delicate, thread-like filaments that crisscross the glowing gas. Understanding this magnetic maze is one of the most challenging frontiers in astrophysics, as it requires us to decode the subtle clues these invisible forces leave behind. Imagine trying to map the wind by watching how it bends a field of wheat. Astronomers use a similar, elegant technique to chart these cosmic magnetic fields, a method known as polarimetry. It all starts with the light from the nebula's bright stars. This light travels to us as a wave vibrating in all directions. However, as it journeys through the vast clouds of the nebula, it encounters countless tiny, elongated dust grains that are aligned by the local magnetic field, all pointing in the same direction like countless microscopic compass needles. When the starlight strikes these aligned grains, they preferentially scatter light that vibrates in one particular direction, effectively filtering it. By the time this light reaches our telescopes, it has become polarized, meaning its waves are now predominantly vibrating in a single plane. The specific orientation of this polarized light acts as a direct arrow, pointing perpendicular to the direction of the magnetic field that aligned the dust grains. By meticulously measuring the polarization of starlight from thousands of stars both within and behind the nebula, astronomers can painstakingly reconstruct a detailed map of the magnetic field structure, revealing how it bends and twists throughout the entire region. One of the most dramatic roles of this magnetic web is to act as a cosmic support structure, a hidden skeleton that holds vast clouds of gas against the crushing force of their own gravity. A molecular cloud like the one that birthed Orion contains enough material to collapse under its own weight in a relatively short time. But the observed rate of star formation is much slower than this simple calculation would suggest. The missing piece of the puzzle is magnetic support. The field lines permeating the cloud exert a powerful pressure that pushes back against gravitational collapse. Picture a dense cloud of gas trying to fall inward, but being cradled and held aloft by a vast network of magnetic springs. This support is not absolute. It simply regulates the collapse, ensuring that star formation is a slow, controlled process rather than a rapid, catastrophic implosion. It's this magnetic braiding that gives the nebula its delicate, filamentary appearance, with tendrils of gas stretched along the field lines like iron filings aligning around a magnet. However, this support system can be overcome, and the mechanism for doing so is as fascinating as the support itself. For a star to form, the gas must eventually become dense enough for gravity to win the battle. This happens through a process called ambipolar diffusion. Within a cloud, the neutral atoms and molecules are mostly unaffected by the magnetic field directly. But the few ionized particles atoms that have lost an electron are tightly bound to the field lines, trapped to spiral around them. The magnetic field support is communicated to the neutral gas through collisions with these trapped ions. In the relatively low-density regions of a cloud, this coupling is strong, and the magnetic field effectively holds everything up. But as gas slowly drifts and accumulates in the core of a cloud, the neutral particles become so dense that they start to slip past the trapped ions, much like a crowd of people could slowly flow around a few fixed posts. This gradual slippage of neutral gas through the stationary magnetic field allows material to drain into the central core, increasing its density until gravity finally becomes strong enough to trigger a runaway collapse and the birth of a new star. Beyond simply supporting or resisting collapse, magnetic fields are the ultimate choreographers of the nebula's most dynamic flows. They are the invisible channels that guide and collimate the powerful bipolar jets we see in Herbig-Haro objects. As material falls onto a newborn star from its surrounding disk, it drags the magnetic field lines with it, winding them up into an incredibly tight, powerful structure. This magnetic slingshot, concentrated at the star's poles, acts like a nozzle on a garden hose, focusing the chaotic infall of material into two narrow, high-velocity beams that shoot out in opposite directions. Without these magnetic fields to channel and focus the outflow, the energy from a young star would be expelled in a weak, spherical wind, utterly incapable of carving out the vast, luminous structures we observe. The magnificent alignment of many of these jets over large distances in Orion is a direct testament to the ordered structure of the large-scale magnetic field that pervaded the original cloud, a fossilized imprint of the conditions present at the cluster's birth. The interplay between magnetic fields and the intense radiation from massive stars creates a feedback loop that continuously reshapes the nebula. The powerful stellar winds and radiation pressure from stars like those in the trapezium cluster exert an immense force, relentlessly pushing against the surrounding gas and magnetic field structure. In some regions, the magnetic field is strong enough to resist this pressure, helping to maintain the integrity of dense pillars and filaments. In other areas, the stellar onslaught overwhelms the magnetic support, effectively blowing the field lines apart and dispersing the gas along with them. This constant tug of war between magnetic, gravitational, and radiative forces is what creates the nebula's stunning complexity: the sharp ridges, the evaporating globules, and the vast ionized cavities. The magnetic field is the unsung hero in this cosmic drama, a resilient yet flexible framework that provides both the stability for stars to form and the structure through which the nebula's brilliant but destructive power is expressed, a fundamental force silently guiding the evolution of this celestial masterpiece from behind the scene. But beyond the scientific data and the physical laws, the Orion Nebula holds a different kind of power over the human imagination, one that reaches back into our deepest past and stretches forward into our most speculative futures. This is the enigma often referred to in more speculative circles as the Orion ID mystery, a collection of historical, mythological, and outright fringe interpretations that ask not just what the nebula is, but what it might mean. For as long as humans have looked up and seen the smudge of light in the hunter's sword, we have been trying to inscribe our own stories upon it, transforming this cloud of gas and dust into a canvas for our myths, our fears, and our most profound hopes. To explore this is to journey through a parallel universe of thought where astronomy meets archaeology and where scientific discovery tangles with the enduring human desire to find pattern, purpose, and connection in the cosmos. Our story begins not with telescopes, but with the naked eye wonder of ancient civilizations. The constellation of Orion itself has been a celestial landmark for millennia, recognized by cultures across the globe. The fuzzy patch we now know as the nebula was often integrated into these cosmic pictures. For the ancient Greeks, it was part of the sword or club wielded by the great hunter Orion. But other cultures saw far more. Perhaps the most striking and often cited interpretation comes from the Maya of Mesoamerica. They saw the trio of stars forming Orion's belt not as a belt at all, but as a celestial hearth, a trio of stones used for cooking. And the Orion Nebula itself, they named it Xibalba B, or the road to the underworld. In their cosmology, this glowing cloud was a portal, a smoky entrance to the realm of the gods and the dead. This wasn't a casual nickname. It was a central part of their spiritual understanding of the universe, a place where the veil between worlds was thin. It's a breathtakingly prescient idea that this nebulous region was a gateway, even if its meaning was entirely mythological rather than astronomical. This theme of the nebula as a significant cosmic location was powerfully resurrected in the 20th century, but with a dramatic new twist. In the 1970s, author Robert K.G. Temple published his controversial book, The Sirius Mystery, which, while focused on the star Sirius, popularized the idea that the ancient wisdom of the Dogon people of Mali contained accurate astronomical knowledge they should not have possessed, supposedly given to them by visitors from the Sirius system. This spawned a wider fascination with connecting ancient civilizations to extraterrestrial influences, and Orion, being one of the most prominent constellations, was a natural focal point. Soon, a more specific theory emerged, suggesting that the three pyramids of the Giza Plateau in Egypt were a terrestrial mirror of the three stars of Orion's belt. Proponents of this Orion correlation theory argued that the arrangement was too precise to be coincidence, and that the ancient Egyptians were either mapping the heavens with impossible accuracy, or were perhaps even signaling their own celestial origins, with the Milky Way representing the Nile River and the Great Pyramid acting as a kind of landing beacon or monument to a connection. Orion beings, while this idea is captivating and has been featured in numerous documentaries and books, it's crucial to separate the compelling narrative from the archaeological and astronomical facts. Mainstream Egyptologists point out that the pyramid's alignment has clear and well understood solar and stellar orientations within the context of Egyptian religion, primarily linked to the pharaoh's journey to join the god Osiris in the afterlife. The match between the pyramids and Orion's belt, while visually interesting, is not perfect. The relative sizes and brightness of the stars don't cleanly correspond to the sizes of the pyramids, and the precession of the Earth's axis means the alignment was actually closer in a period thousands of years before the pyramids were built. The theory, while a fascinating example of modern myth-making, is generally dismissed by scholars as a form of pattern-seeking. The same human impulse that leads us to see faces in clouds or animals in the stars projecting a modern, extraterrestrial narrative onto ancient cultural achievements. This speculative thread was woven even further with the rise of the ancient astronaut hypothesis. Thinkers like Erich von Däniken proposed that the gods of old were actually advanced spacefaring visitors, and that structures like the pyramids were not just tributes to the stars, but functional artifacts of alien technology. Within this framework, the Orion Nebula's role evolved from a symbolic gateway to a literal one. Some speculated that it wasn't just a stellar nursery, but a stargate, a natural or artificial wormhole that could allow for instantaneous travel across the galaxy. The nebula's turbulent, energetic heart was reimagined as the engine for this cosmic transit system, with its intense radiation and magnetic fields providing the power to stabilize a hyperspace corridor. This idea, though entirely in the realm of science fiction without a shred of empirical evidence, taps into a powerful and enduring human fantasy, the desire for a universe that is not only inhabited but interconnected, where the vast distances between stars are not an impassable barrier but a highway. The most scientifically adjacent, yet still highly speculative, angle in this mystery involves the search for extraterrestrial intelligence, or SETI. If we were to search for a beacon, a deliberate message from an advanced civilization, where would we look? Some researchers have playfully suggested that certain cosmic locations might serve as libraries or billboards. The Orion Nebula, as one of the closest, brightest, and most active star-forming regions, would be a prime candidate for such a landmark. The idea is that any long-lived spacefaring culture might use such a prominent and persistent feature as a natural meeting point or a repository for knowledge, perhaps by modulating its light in some subtle, technological way or by placing artifacts within it. While no such signal or artifact has ever been found, and most mainstream SETI efforts focus on listening to specific stars, the notion persists that the nebula's very prominence makes it a compelling place to look for evidence that we are not alone, blending the lines between rigorous science and boundless curiosity. So, how do we reconcile these captivating stories with the hard, physical reality of the Orion Nebula? The answer lies in appreciating the dual nature of this celestial object. Scientifically, it is a laboratory of physics and chemistry, a place governed by gravity, radiation, and magnetic fields. Its story is written in the language of spectral lines and thermal emissions. But culturally and psychologically, it is a mirror. The Orion ID mystery is not about the nebula itself, but about us. It reflects our innate need to find meaning, to connect with the cosmos on a personal level, and to wonder if we are part of a larger story. The ancient Maya saw an entrance to the spirit world because they were mapping their spiritual beliefs onto the heavens. Modern theorists see a stargate because we are a technological species dreaming of interstellar travel. These interpretations, though factually incorrect, are profound in their own right. They show that the Orion Nebula has served as a constant Rorschach test for humanity, a luminous inkblot in the sky upon which we project our deepest questions about life, death, and our place in the universe. The true mystery isn't whether the nebula is a gateway. It's that for thousands of years across countless cultures, it has consistently inspired us to believe that gateways are possible. Yet for all its current grandeur and turbulent activity, the Orion Nebula is living on borrowed time, a magnificent but temporary structure in the cosmic landscape. The very forces that make it visible, the blistering ultraviolet radiation and powerful stellar winds from its most massive stars, are the same forces that are methodically dismantling it. This is the great paradox of Orion. It is both a stellar cradle and a stellar demolition site, and the demolition is winning. The brilliant trapezium stars are not just illuminating the nursery, they are evaporating it, and in doing so, they are ensuring their own birthplace will be completely erased within a cosmically brief few million years. The future of Orion is not one of continued creation, but of gradual dispersal, leading to a final, beautiful, and starkly different phase of life. The primary engine of this dissolution is photoevaporation, a relentless process we've seen on a small scale in the Proplyds, but which is occurring across the entire nebula. The immense flood of ultraviolet photons from stars like Theta1 Orionis C acts like a cosmic blowtorch, striking the vast clouds of neutral hydrogen gas that make up the bulk of the nebula. Each photon carries enough energy to violently strip an electron from a hydrogen atom, a process called ionization. This doesn't just make the gas glow, it also heats it to temperatures of around 10,000 degrees Celsius. This superheated, ionized gas exerts a tremendous pressure, and since it is no longer gravitationally bound to the dense, cold molecular cloud from which it came, it simply expands outward into the vacuum of space, streaming away from the nebula in a vast, invisible wind. It's akin to boiling a pot of water. The heat transforms the liquid into a gaseous steam that escapes into the air. In Orion, the entire nebula is the pot, and the trapezium stars are the furnace, steadily converting the raw material of future stars into an expanding, diffuse fog that will eventually merge with the general interstellar medium. Adding tremendous force to this evaporative wind is the physical pressure from the stellar winds themselves. These are not just photons of light, but actual particles, a hurricane of protons and electrons being ejected from the surfaces of the massive stars at speeds of several thousand kilometers per second. This torrent of charged particles physically rams into the surrounding gas, pushing it outward and helping to carve out the vast cavities we see as the X-ray superbubbles. This combination of radiation pressure and wind pressure creates a powerful feedback loop that is extraordinarily efficient at clearing out a region of space. The process is self-reinforcing. As the gas is blown away, the path is cleared for more radiation and wind to reach deeper into the cloud, attacking denser regions that were previously shielded and accelerating their evaporation in turn. The beautiful, sculpted pillars like the Mystic Mountain are the last bastions of this resistance, their dense cores temporarily withstanding the onslaught even as their outer layers are being shredded and blown into the void. We can already see the direct evidence of this mass loss happening in real time. Spectroscopic observations reveal that the ionized gas on the near side of the nebula is moving toward us, while the gas on the far side is moving away. This is the clear signature of a global expansion, a ballooning of the entire H2 region as it is inflated from within by the pressure of the hot, ionized gas. The nebula is quite literally blowing itself apart. Furthermore, by measuring the total luminosity of the ionizing stars and the amount of glowing gas, astronomers can calculate the rate of this mass loss. The numbers are staggering. The nebula is losing mass equivalent to our entire sun every few tens of thousands of years. While the total mass of the nebula is still immense, this relentless bleeding cannot continue forever. The reservoir of dense gas is finite, and the erosion is proceeding faster than new stars can form from what remains. The ultimate fate of Orion, therefore, is already written in the motions of its gas and the brilliance of its dominant stars. In a relatively short time, just a few million years from now, the demolition will be complete. The vast, swirling clouds of glowing gas and dark, obscuring dust will have been entirely blown away, scattered across light years of interstellar space. What will be left is the brilliant, naked Orion Nebula cluster, a sparkling collection of stars no longer veiled by their birth cocoon. The cluster will look strikingly similar to the Pleiades or the Hyades, the famous open clusters we see elsewhere in our galaxy. The trapezium stars will still be there, shining brightly, but they will be surrounded by the thousands of lower mass stars that formed alongside them, all now exposed to the blackness of space. The beautiful, ethical glow will be gone, replaced by the sharp, clear points of starlight against an empty backdrop. This transformation has profound implications for the cluster itself and for any remaining planetary systems. Once the protective blanket of gas and dust is removed, the stellar population will be exposed to the full harshness of the galactic environment. The intense radiation that was once absorbed by the nebula will now stream outward unimpeded. More importantly, the removal of the nebula's gas will fundamentally change the gravitational dynamics of the cluster. The vast cloud of gas provided a gravitational potential well that helped to bind the stars together. When that mass is lost, the cluster's gravitational glue is significantly weakened. This often leads to a process known as cluster evaporation, where the gentlest gravitational nudges between stars over millions of years give the lower mass members enough velocity to escape the cluster's dwindling pull. The brilliant, tight-knit trapezium cluster will likely slowly dissipate, its stars drifting apart to join the vast population of isolated field stars in the galactic disk. The family will be broken up, its members sent on solitary journeys across the galaxy. For any planets that manage to form in this chaotic nursery, the unveiling of the cluster presents a new chapter. On one hand, the end of the photoevaporative threat means their planetary atmospheres are no longer at risk of being boiled away by external radiation. Their orbits, which may have been destabilized by the gravitational pull of the nebula's uneven gas distribution, will settle into more predictable paths. On the other hand, these planetary systems will now exist in a more exposed and perhaps lonely state. The stunning celestial vistas of glowing gas clouds would vanish from their skies, replaced by the brilliant, close-packed light of neighboring stars, which would themselves gradually fade and spread apart over eons. The end of the nebula marks the beginning of maturity for these systems, a quiet, stable existence that stands in stark contrast to the violent, radiant chaos of their birth. The story of Orion's fading future is a universal one, a standard chapter in the life cycle of all giant molecular clouds. They are not permanent features of the galaxy, but temporary, vibrant blossoms that erupt with stellar life and then fade away, their material recycled to form future generations of stars and planets. Our own sun was likely born in a similar cluster 4.6 billion years ago, within a nebula that has long since vanished, its stars scattered across the local galaxy. By studying Orion's inevitable fate, we are looking back at our own origins. The nebula's transient beauty is a powerful reminder of the dynamic, ever-changing nature of the cosmos, where even the most magnificent structures are merely waypoints in a grand billion-year cycle of creation, destruction, and renewal. Its eventual disappearance is not a tragedy, but a natural and necessary conclusion, paving the way for the next cosmic blossom to bloom elsewhere in the fertile disk of our Milky Way. This grand cycle of creation and destruction we've witnessed throughout the nebula points to an even deeper, more fundamental process at work, one that connects the life of Orion directly to our own existence. This is the phenomenon of cosmic recycling, where the nebula acts as a galactic foundry, taking the ashes of long-dead stars and forging them into the raw materials for new suns, planets, and the potential for life itself. The very atoms that make up our bodies, the iron in our blood, the calcium in our bones, and the oxygen we breathe, were all created in the hearts of stars that lived and died billions of years ago, and a place like the Orion Nebula is one of the primary factories where this ancient stardust is gathered and put to work once more. To understand this, we need to look at the elemental ingredients of the cosmos. In the beginning, after the Big Bang, the universe was a much simpler place, composed almost entirely of just two elements, hydrogen and helium, with a tiny trace of lithium. These were the only building blocks available for the very first generation of stars. Those primordial stars, often called population 3 stars, were colossal behemoths that burned hot and fast. Within their searing cores, the nuclear furnaces did more than just fuse hydrogen into helium. Under immense temperatures and pressures, they began to forge heavier elements. They fused helium into carbon, carbon into oxygen, and through a complex chain of nuclear reactions known as stellar nucleosynthesis, they built up a periodic table of elements all the way up to iron. This process of creation was also a death sentence. Once a star's core becomes iron, fusion can no longer release energy, it starts to consume it. For the most massive of these early stars, this led to a catastrophic collapse and a supernova explosion of unimaginable power, an event so violent that it forged elements even heavier than iron, like gold, silver, and uranium. and then blasted this newly cooked material out into the void, seeding the pristine hydrogen and helium clouds with this rich elemental pollution. The Orion Nebula is a direct beneficiary of this ancient legacy. The gas and dust that we see glowing and swirling today is not the pristine gas of the early universe. It is enriched gas carrying within it the chemical fingerprints of countless generations of stars that lived and died over the billions of years before our solar system even formed. When astronomers perform a detailed chemical analysis of the nebula's composition, they find clear and abundant evidence of these heavier elements, often referred to collectively as metals in astronomical terms. They detect the spectral signatures of oxygen, carbon, nitrogen, silicon, and iron, all suspended within the cloud. This enriched material is the cosmic compost, the fertile soil from which the next generation of stars and planets will grow. The presence of these elements is the definitive proof that we are not looking at the first act of star formation, but a later chapter in a continuous, galaxy-wide cycle of death and rebirth. This enrichment process is not a gentle sprinkle, it is a dynamic and ongoing infusion. We've already explored the evidence for ancient supernova whose shock waves may have triggered the very formation of the trapezium cluster. Those explosions were the delivery mechanism, the cosmic trucks dumping a fresh load of heavy elements into the neighborhood. But the enrichment continues even now through the steady, relentless winds from the massive stars currently shining. Stars like Theta1 Orionis C are constantly fusing hydrogen into helium and heavier elements in their cores. Their powerful stellar winds act like a constant, high-speed conveyor belt, carrying this newly processed material away from the star's surface and injecting it directly into the surrounding nebula. This isn't as dramatic as a supernova, but it is a continuous and efficient way to pollute the local environment with elements like carbon and oxygen, ensuring that the gas used to form the next round of low-mass stars is even richer than the last. The most profound consequence of this cosmic recycling is its direct connection to the formation of planets and the potential for life. Let's consider the humble Proplyd, the protoplanetary disk surrounding an infant star. Before the process of enrichment, a disk would have been composed only of hydrogen and helium gas with virtually no solid material. It would have been incapable of forming rocky planets. But in an enriched nebula like Orion, the story is completely different. The dust grains within these disks are not just simple ices. They are microscopic particles of silicates similar to sand and grains of carbon similar to soot. These tiny solid seeds are the direct descendants of stardust, and they are absolutely essential for planet formation. They act as condensation nuclei, allowing the gas in the disk to stick together, first into tiny pebbles, then into planetesimals, and eventually into full-sized terrestrial planets like Earth, Mars, and Venus. Furthermore, the incredible chemical diversity we find in places like the Orion hot core, with its complex organic molecules, is only possible because of this elemental enrichment. Molecules like methanol, formaldehyde, and even simple sugars are built from carbon, oxygen, and hydrogen atoms. Without that initial carbon, forged in a star that died long ago, this complex chemistry simply could not occur. The presence of these probiotic molecules means that a planetary system forming in Orion doesn't start from scratch. It is born pre-loaded with the basic chemical hardware for life. The water for its oceans, the carbon for its organic molecules, and the minerals for its rocky crust are all inherited gifts from the stellar generations that came before. When a new sun-like star ignites within the nebula, the planetary system that forms around it will literally be built from the ashes of its ancestors, a cosmic inheritance that provides all the necessary ingredients for a world that could one day support biology. This grand perspective forces us to see the Orion Nebula not as an isolated island in space, but as a vital organ in the living body of our galaxy. It is a key node in the galactic ecosystem, a place where the galaxy breathes in the dispersed, enriched gas from past stellar deaths and breathes out new stellar and planetary systems. This cycle is the engine of galactic evolution. With each passing generation, the overall metal content of the galaxy slowly increases. The stars that form today are, on average, richer in heavy elements than the stars that formed 5 billion years ago, and vastly richer than the very first stars. Our own Sun is a product of this process, a third or fourth generation star that formed from a cloud that had been seeded by the supernova of its predecessors. This is why our solar system contains such a wealth of elements, allowing for the formation of a rocky, water-rich planet that could eventually become a home for life. The Orion Nebula, therefore, offers us a profound and deeply humbling connection to the cosmos. The calcium in your bones was forged in the heart of a red giant star. The iron that carries oxygen in your blood was created in the last moments of a supernova. The carbon that forms the backbone of every organic molecule in your body was synthesized in a star that shone brightly long before our Sun was born. We are not just living in the universe, we are literally made of it. We are stardust that has coalesced, become conscious, and is now looking back out at the very nurseries where new stardust is being prepared for future worlds and perhaps future life. The brilliant glow of the Orion Nebula is more than just a beautiful light show. It is a visible testament to this continuous billion-year cycle of renewal, a constant reminder that we are an intimate part of a vast, dynamic, and ever-recycling cosmos. But to truly comprehend the Orion Nebula in its entirety, we cannot rely on the limited view offered by our own human eyes. The spectacular vista of glowing gas and dark dust that we see in famous Hubble images represents only a single, narrow slice of the nebula's full story, a story that is written across the entire electromagnetic spectrum. When we train telescopes that can see in infrared, radio, and X-ray light upon this cosmic nursery, the familiar landscape transforms, revealing a hidden universe of activity, structure, and violent energy that is completely invisible in optical light. This multi-wavelength approach is the cornerstone of modern astronomy, peeling back layer after layer of cosmic reality to expose the fundamental processes that shape the cosmos. The first and most dramatic transformation occurs when we switch from visible light to the infrared. Our optical view is famously blocked by the nebula's abundant dust. The dark lanes and pillars are opaque curtains that hide the most active sites of star birth. But infrared light, with its longer wavelengths, acts like a cosmic skeleton key. It slips effortlessly between the tiny dust grains that so effectively block visible light, allowing us to peer straight through the obscuring veils and into the heart of the densest clouds. The result is a revelation, where Hubble saw the dark, imposing form of the Mystic Mountain. An infrared telescope like the James Webb Space Telescope sees a structure that is practically glowing from within. The dark pillar becomes semi-transparent, and blazing from its core are the intense, warm lights of newborn stars still embedded in their dusty cocoons. The entire nebula, which appears as a hollowed-out shell in visible light, is revealed in infrared to be packed solid with thousands of previously hidden young stellar objects, turning the familiar image of Orion from a scenic landscape into a densely populated stellar metropolis, proving that the majority of the star formation action is happening behind the scenes, hidden from our conventional view. Beyond simply revealing hidden stars, infrared observations are indispensable for studying the cold components of the nebula. The dust grains themselves, which are only about -260 degrees Celsius, are far too cold to emit visible light, but they glow brightly in the mid and far infrared. This allows astronomers to map the total mass and distribution of the nebula's solid material, the very stuff from which planets are made. Furthermore, as we've seen with the unidentified infrared bands, specific molecules in the gas phase, including complex organic compounds, have their own unique vibrational signatures in the infrared. By analyzing this infrared fingerprint, scientists can conduct a remote chemical census, identifying the molecular building blocks floating within the cloud and understanding how they are distributed in different environments, from the harsh surface of the Orion bar to the sheltered depths of the molecular core. The infrared view transforms the nebula from a simple painting of light and shadow into a rich chemical and thermal map, detailing both the hidden stellar population and the frigid raw materials that surround them. When we tune our instruments even further into the radio part of the spectrum, we unlock the ability to listen to the subtle motions and magnetic whispers of the nebula's cold, neutral gas. Radio waves have the longest wavelengths of all, allowing them to pass through dust clouds with virtually no resistance, probing the deepest, darkest, and coldest recesses of the molecular cloud where even infrared light begins to fade. The primary targets for radio astronomers are specific molecules, most notably carbon monoxide. Every type of molecule can rotate at specific frequencies, and when it shifts from a higher rotational state to a lower one, it emits a photon at a very precise radio wavelength. By tuning a radio telescope to the frequency of, say, carbon monoxide, astronomers can trace the distribution and motion of this gas throughout the entire Orion complex, mapping the vast, invisible molecular reservoir that extends far beyond the bright, visible nebula. But the power of radio astronomy goes far beyond mere mapping. Because of the Doppler effect, these molecular emission lines are not perfectly sharp, they are broadened and shifted. By meticulously measuring these subtle changes in wavelength, scientists can determine the velocity of the gas with phenomenal precision. They can see vast streams of cold material flowing inward to feed newborn stars, detect the turbulent, chaotic motions within dense cores on the verge of collapse, and trace the high-velocity outflows from protostars as they blast through the surrounding cloud. This turns the radio data into a dynamic, three-dimensional movie of the nebula's internal motions. Additionally, as we discussed with polarimetry, radio telescopes can measure the polarization of the light emitted by dust grains aligned by magnetic fields, allowing us to finally chart the invisible magnetic skeleton that guides the flow of gas and the birth of stars, revealing the fundamental force that provides the nebula with its intricate filamentary structure. The final piece of this multi-wavelength puzzle comes from the most energetic end of the spectrum, X-rays. If the infrared view shows us the hidden stars and the radio view shows us the cold gas, then the X-ray view reveals the nebula's seething, violent heart. Space telescopes like Chandra peer not at starlight or cold dust, but at the truly extreme processes within the nebula. The primary sources of this high-energy radiation are the massive young stars themselves. The surfaces of these stellar giants are riddled with colossal magnetic storms and superheated flares, far more powerful than anything our sun produces. These events can heat patches of the stellar atmosphere to tens of millions of degrees, causing them to blaze with intense X-rays. So, while these stars look like steady points of visible light, in X-rays they appear as wildly variable, brilliant beacons of high-energy activity. But perhaps the most surprising discovery from X-ray observatories has been the sheer abundance of X-rays coming from the nebula's population of young, sun-like stars. Before these observations, it was assumed that low-mass stars would be relatively quiet in X-rays. The data revealed the opposite. These infant suns are incredibly X-ray bright, often thousands of times more luminous in X-rays than our middle-aged sun. This intense activity is a hallmark of stellar youth. These stars are rapidly rotating and possess incredibly strong magnetic dynamos, which drive powerful flares and heat their outer coronae to temperatures of several million degrees. This pervasive X-ray glow has profound implications for the planetary systems forming around these stars. The intense high-energy radiation can profoundly affect the chemistry of the surrounding protoplanetary disk, potentially vaporizing ices and driving chemical reactions that would not occur under milder conditions. and it could even play a role in either promoting or threatening the development of prebiotic chemistry on any nascent rocky worlds. Beyond the stars themselves, Chandra revealed the vast, diffuse X-ray glow of the superbubbles we discussed earlier, the gigantic cavities of million-degree gas that have been inflated by the combined power of stellar winds and supernova explosions. This diffuse emission paints a completely new picture of the nebula's large-scale structure, showing the titanic forces that are actively blowing the nebula apart from the inside out. The multi-wavelength portrait of the Orion Nebula is therefore not just a collection of pretty pictures, it is a suite of powerful diagnostic tools. Each wavelength band probes a different physical condition. Optical light shows us the photosphere of stars and fluorescing gas. Infrared reveals warm dust and hidden young stars. Radio maps the cold, dense gas and magnetic fields. And X-rays expose the superhot plasma and violent magnetic activity. By combining all these views, astronomers can construct a complete, holistic model of this stellar nursery, understanding its energy budget, its life cycle, and the interconnected physics that govern everything from the collapse of a gas cloud to the formation of a planet. It is a masterclass in how modern science must look at the universe with all its available eyes to see the full, magnificent, and often hidden picture. Given the violent, radiant environment of the Orion Nebula, you might wonder if planets could possibly form and survive in such a chaotic stellar nursery. The answer is a fascinating and paradoxical yes. But the worlds that emerge from this cosmic crucible would be nothing like the tranquil, life-nurturing oasis of Earth. The process of planet formation here is a high-stakes race against time, set against a backdrop of relentless stellar radiation and gravitational turmoil that forges a collection of some of the most exotic and bizarre worlds we can imagine. While our solar system formed in a relatively quiet, isolated corner of the galaxy, a planetary system born within the Orion Nebula would be shaped by forces of almost unimaginable intensity, leading to architectural wonders and horrors unlike anything we see in our own neighborhood. The first and most formidable challenge for any nascent planet is the same ultraviolet radiation that makes the nebula glow. This energy flood acts like a cosmic blowtorch directed at the protoplanetary disks surrounding infant stars. In a process called photoevaporation, the intense UV light from massive stars like those in the trapezium cluster heats the outer layers of these gas and dust disks, boiling the material away and stripping it back into the nebula. This creates a dramatic deadline for planet formation. A gas giant like Jupiter, which requires a massive envelope of hydrogen and helium, must form incredibly quickly, gathering its gas before the entire disk is vaporized by the external onslaught. This intense pressure favors the rapid formation of planets very close to their host stars, in regions where the star's own gravity can help shield the material from being blown away. The result is a preponderance of what astronomers call hot Jupiters, gas giant planets that orbit astonishingly close to their suns, completing a full revolution in a matter of days or even hours. Imagine a world like Jupiter, but so close to its star that its atmosphere is seared to a temperature of thousands of degrees. The nebula's harsh conditions make these blistering giants far more common here than in calmer regions of space. Their formation is a story of cosmic migration. A gas giant core might begin forming in the cooler, outer regions of the disk, but the photoevaporative wind blowing from the outside in, combined with gravitational interactions with other forming planets or even passing stars in the dense cluster, can force these nascent giants to spiral inward, settling into a scorchingly close orbit. On such a world, the very concept of a solid surface would be irrelevant. You would find a vast, turbulent atmosphere of incandescent gas, where elements like silicon and iron are vaporized into clouds, and where it might literally rain liquid rock or rubies. The relentless stellar winds from the nebula's massive stars would continuously buffet these worlds, potentially stripping away their outer atmospheres and leaving behind comet-like tails of lost material stretching across the void. For smaller, rocky planets attempting to form, the environment is even more perilous. The raw materials for a terrestrial world, the dust grains of silicates and metals, are certainly present. However, the photoevaporation process can truncate the protoplanetary disk, robbing it of the vast reservoir of material in its outer reaches. This could result in planetary systems that are compact and resource-poor, with rocky worlds that are generally smaller and drier than Earth. Any water ice that would normally be available in the outer disk to later deliver water to inner planets via comet impacts would be vaporized and blown away long before it could reach the inner system. This suggests that ocean worlds like our own might be exceptionally rare in such a radiant environment. Instead, the rocky planets that do manage to coalesce might be dense, metal-rich worlds, perhaps resembling a vastly larger version of Mercury, with vast plains of solidified lava and a surface scoured clean of any volatile compounds by the perpetual ultraviolet bath. The exotic chemistry of the nebula itself, however, opens the door to worlds with compositions that are truly alien. We know from studying regions like the hot core that the molecular cloud is rich with complex compounds, including carbon-bearing molecules. In a disk surrounding a carbon-rich star, this could lead to the formation of carbon planets, worlds where silicon carbide takes the place of Earth silicates, and where the surface could be covered in mountains of graphite and deposits of diamond. Even more fantastically, on a world orbiting close to a hot star, the extreme temperatures could lead to clouds made of corundum, the mineral that forms rubies and sapphires condensing in the atmosphere, creating skies that literally glitter with falling gems. The very clouds themselves could be composed of vaporized rock, creating a permanent global haze of silicate droplets that would refract the light of the brilliant trapezium cluster into a perpetual, fiery twilight. The ultimate survival of any planetary system in the Orion Nebula is a question of location and timing. A star that forms on the outskirts of the nebula, or one that is quickly ejected from the dense cluster core, might retain a more normal-looking planetary system. Its architecture spared the worst of the gravitational perturbations and radiation flooding. For those stars that remain in the thick of the action, their planets face a gauntlet of threats beyond just radiation. The dense stellar environment makes close gravitational encounters between stars a common occurrence. A passing star could easily destabilize the delicate orbital dance of planets, flinging them into the cold of interstellar space as rogue planets or sending them careening into their parent star. The planetary systems that do survive to maturity would likely be very different from our own, compact, strange, and forged in a cosmic inferno. While the chances for a calm, Earth-like world in such a place are vanishingly small, the nebula's intense creativity ensures that the planets it does produce are among the most spectacular and extreme examples of what is possible in the universe, proving that where there is matter and energy, worlds will form, no matter how hostile the conditions. And so we arrive at our final, and perhaps most profound, mystery, one that transforms the Orion Nebula from a distant object of study into a personal and deeply resonant part of our own story. This is the nebula's role as a cosmic time machine, a concept that operates on two powerful, interconnected levels. The first is the simpler, yet still mind-bending, fact of light's finite speed. The photons that left the trapezium cluster and are now striking the mirrors of our telescopes began their journey over 1,300 years ago. When we gaze at an image of Orion, we are not seeing it as it is now, but as it was during the twilight of the Roman Empire. We are literally looking into the past, witnessing a chapter of cosmic history that unfolded long before any modern civilization arose to document it. But the second, far more significant way the nebula acts as a time machine is not through the simple delay of its light, but through its very nature. The Orion Nebula is not merely a relic, it is a living, breathing analog of our own origins. It provides us with an unprecedented window into the violent, radiant, and chaotic environment in which our Sun and thousands of other stars like it were born some 4.6 billion years ago. Our solar system is a mature, settled neighborhood. The planets orbit in stable, predictable paths, and the vast nebula of gas and dust that gave them birth has long since dissipated. Its material either incorporated into the planets or blown away by the young sun's first stellar winds. That primordial nursery is gone, leaving behind only forensic clues in the compositions of ancient asteroids and the craters on the moon. In Orion, we have a chance to witness that lost chapter of our own history playing out in real time right before our eyes. Every phenomenon we've explored, from the photo-evaporating Proplyds to the explosive stellar dynamics, is a piece of the puzzle that was our own genesis. When we see a Proplyd being boiled away by the harsh ultraviolet glare of a massive star, we are looking at the kind of existential threat our own infant planetary system may have faced. Did our Sun have massive, disruptive siblings in its birth cluster whose radiation threatened to strip away the volatile materials needed for life? The evidence from Orion suggests this is not just possible but likely. The presence of complex organic molecules in the frigid depths of the molecular cloud core shows us that the basic chemical ingredients for life, the water, the alcohols, the simple sugars, were already present in the raw material from which our solar system condensed. We are seeing the delivery system for our own oceanic and probiotic chemistry being assembled before our eyes. This perspective fundamentally changes the questions we ask. We are no longer just studying a beautiful object in space. We are conducting a form of cosmic archaeology, using Orion as a dig site to uncover the conditions of our own creation. By measuring the distribution of ages in the Orion Nebula cluster with its mix of older and younger stars, we learn that star formation is not a single, brief event, but a protracted, multi-generational process. This tells us that our Sun was likely not an only child, but was born into a large, extended family of stars, many of which have long since drifted away across the galaxy. The gravitational billiards game we see in the BN/KL outflow and the runaway stars like Theta1 Orionis C demonstrate the kind of violent interactions that would have profoundly shaped the architecture of any nascent planetary systems, potentially flinging worlds into deep space or sending comets showering inward. The very structure of our solar system, with its outer cloud of icy comets, might be a direct result of such gravitational nudges from long-lost stellar siblings. Ultimately, the greatest gift the Orion Nebula gives us is context. It places our own story within the grand, universal narrative of stellar and planetary life cycles. We see that our solar system is not a unique, special creation, but one of countless possible outcomes from a common, dynamic, and often violent process. The same forces of gravity, radiation, and chemistry that are sculpting Orion today are the very forces that built our world and filled it with the elements necessary for life. The calcium in our bones, the iron in our blood, and the carbon in our DNA were all forged in the hearts of stars that lived and died long before the Sun was born, and their ashes were scattered into nebulae just like this one. When we look at the Orion Nebula, we are not just looking at a distant cloud. We are looking into a mirror that reflects our own deepest past, a swirling, luminous portrait of our own cosmic ancestry, reminding us that we are, in the most literal sense, children of the stars. So, as our journey through this cosmic tapestry draws to a close, let's take one final, sweeping look at the breathtaking parade of wonders we've encountered. We began with stellar speedsters carving bow shocks into the Nebula Sea and infant solar systems, the Proplyds, locked in a dramatic race for survival against the blistering radiation of their massive neighbors. We ventured into the shadowy embrace of the Great Dark Lane, a cold river of dust hiding future stars, and met the nebula's brilliant but runaway monarch, Theta1 Orionis C, whose turbulent past shapes the entire region. We witnessed the cosmic gunfight of the Orion Bullets and the brilliant tantrums of newborn stars in Herbig-Haro objects, their jets painting luminous scars across the void. We then decoded the universe's chemical language, from the pervasive, unexplained fingerprint of the unidentified infrared bands to the natural laser light of water mazes, pinpointing the violent birth of stars. We explored the razor-sharp frontier of the Orion Bar, a cosmic laboratory where light forges complex molecules, and the explosive outbursts of Fu Orionis stars, where a star's feeding frenzy transforms it into a beacon. We uncovered the ghostly evidence of silent supernova, stellar deaths that left behind no corpse, and listened to the faint microwave whisper of spinning nanodiamonds. We delved into the frigid, chemical-rich heart of the Orion molecular cloud, a factory for life's precursors, and stood in awe of the BN/KL outflow, the shrapnel from a catastrophic stellar collision. We learned to see through the cosmic filter of Orion's veil, discovered the seething chemical crucible of the hot core, and marveled at the majestic, eroding pillars of the mystic mountain, which shelter new stars even as they are destroyed. We navigated the chaotic stellar metropolis of the Orion Nebula cluster, a gravitational mosh pit hostile to stable planets, and deciphered the forbidden light that reveals the nebula's profound emptiness. We reflected on the ancient illusion of Orion's Sword, a fuzzy patch that transformed into a place, and pondered the dark, simple Bok globules, the quiet cradles of sun-like stars. We unraveled the age paradox of multiple stellar generations and beheld the colossal X-ray superbubbles, the invisible architects blowing the nebula apart. We mapped the invisible magnetic maze that guides the flow of creation and explored the speculative Orion ID mystery, where human imagination has long seen gateways and guards. Finally, we faced the nebula's fading future, a testament to cosmic recycling, and saw in its multi-wavelength portrait a hidden universe, while contemplating the bizarre planets forged in its violent crucible. From stellar bullets to chemical factories, from silent supernova to spinning diamonds, each phenomenon is a vital piece of a single grand story. The story of how a cloud of gas and dust becomes stars, planets, and potentially life itself. The Orion Nebula is not a static postcard. It is a living, breathing, dynamic entity, one of the most active and mysterious places in our entire galaxy. It is a constant reminder that the universe is a place of relentless change and breathtaking creativity. So, the next time you find yourself under a clear, dark sky, take a moment to find the constellation of Orion. Look for the 3 stars of his belt, and just below you'll see the faint, glowing smudge of his sword. Now you know that within that tiny, hazy spot lies a cosmic metropolis, a realm of titanic forces and profound mysteries. I'd love to hear which of these 30 phenomena captured your imagination the most. Was it the violent stellar collisions, the hidden chemical laboratories, or the eerie, silent ghosts of dead stars? Share your thoughts in the comments below, and when you look up at Orion's Sword, may you see it with new eyes, filled with the wonder of